Morning.
Morning, Stipo. Let's.
Henry.
Oh, we got 4 and see attendees coming. Okay, let's wait a few. I guess if you don't mind, let's wait a few minutes and let people drop in.
Sure.
9 o'clock, so early time for tech students.
Tell me about it, yeah. Do you want me to try sharing the screen to see if everything works?
Yeah, go ahead.
Okay.
Looks good to me.
You can see that?
Yeah.
Okay.
The animations are working too.
Good. Okay. Stop sharing for a moment. Thank you for the invitation to present here.
Of course. I'll be back in just a minute. I'm gonna wash my hands. What do you say? Give until 9:05? Well, we have all the panelists here. Almost all of them.
Strange, the panelists are in the attendees.
Yeah. Let's see. Let's see. Oh, I can do promote to panelist. That's interesting. Then the question is, oh, I know everyone wants to sleep on a Sunday or on a Friday. And I hope no one minds, but I was planning on recording these so we could post them on our webpage later.
Sounds good. I give you permission, I guess.
Okay, well, it is 9:05, so let's get started, I guess. Hopefully more attendees drop in throughout the day. So for those of you who don't know Stipo, he is a postdoc in, or yeah, you are still a postdoc in the physics department, right? No, okay.
No.
You are working for what, the New Mexico Water Consortium?
Yes, Climate and Water Consortium, yeah.
Okay, so you're now working for the New Mexico Climate and Water Consortium, and he's going to be giving a talk on his research on atmospheric convection, right?
Yes. Okay, let me share my screen and start this. Well, first of all, thank you to the Graduate Student Association for inviting me to give a talk. I participated a lot as a graduate student in the association, so I know how hard it is and how fulfilling it is to be a graduate student. So thank you. Just minimize. Okay. So I'll be talking about the OTRAC field campaign, which is the acronym for Organization of Tropical East Pacific Convection. And why we study there, I'll talk in a little bit, but I'd like to thank Jacob Folkestone and David Raymond for having me as a mission scientist in training during this campaign, where I learned a lot about being a mission scientist and what goes along with it. And it was a real big opportunity. So why do we study convection in atmospheric physics? So if we imagine all of our knowledge about about our atmosphere, I can visualize it as a puzzle. And the tropics make up about 60% of the surface of the planet, located between 30 south and 30 north latitude. And we have a lot of knowledge about the tropics, but we still have a lot of areas that are unexplored. And one of the reasons why it's important to study the tropics is because it influences the weather in the extratropical regions. While it is the constraints that govern the atmosphere in the higher latitudes are the rotation of the planet and the temperature gradient between the tropics and the poles. And that constrains the atmosphere there pretty well, so that there's a lot that we know about those regions. When it comes to the tropics, we need still to know more, and that's why I wanted to focus on studying the tropics. Now, another factor that contributes to this problem of weather prediction and including climate prediction is the lack of observational data. So here are plotted in red the stations on the planet where we get vertical profiles of temperature, moisture, and wind that we put into the models. And you can see that the oceanic regions are quite sparse. There's little data there, and that contributes to our issues. So what we go to is satellite data and assimilating satellite data in our models. Now, the region where we did the OTRAC field campaign here is here in the Eastern Pacific. And there is some data there, as you can see, but over the oceans, we have very little data coverage. So our field campaign was focusing into that region. And one of the reasons is because it's an area where hurricanes, kind of seeds for hurricanes and tropical storms form in the Eastern Pacific. So let's zoom in there and talk more about the conditions in which our field campaign was aimed at. So here in the Eastern Pacific, the shading here shows the sea surface temperature. So in the Eastern Pacific, we have a cold water mass at the equator warming up as we go to the north. So we have a strong sea surface temperature gradient here. And what we wanted to understand is how this sea surface temperature gradient affects the convection that's formed in this region. Another effects that contributes to formation of convection here is the Colombian coast, which is quite mountainous. So there is orography there that influences the flow of air over this region. And on the north side in the Caribbean, we have a pretty uniform sea surface temperature distribution. So these factors really contribute to the fascination about this area and the convection that forms there. So OTRAC was aimed at studying convection in these three areas in these three boxes. So we have the B2 box here on the left, a B1A box, bottom right, and B1B box. So we had the Eastern Pacific box called B2, the Colombian box B1A, and the Caribbean box B1B. And this is the way that we did these flights. We flew, for example, B1A and B1B one day, and then next day we would fly B2. But so why did we do that? The Eastern Pacific region this far region of Eastern Pacific is known to form precursors to tropical storms that traveled up to the United States. So understanding how the convection forms here and what are the influences that control the convection can bring us understanding about tropical storm formation in this region. Another reason is African easterly waves travel from the east through this region, interact with all these effects and environmental factors, and can form tropical storms by crossing over. Sometimes they do, sometimes that they don't. And one of the things that we want to understand what contributes to these African easterly waves turning into tropical storms and what conditions inhibit that. So African easterly waves are known in the Atlantic to form hurricanes in that region. So the OTREC field campaign lasted from 5th of August to October 3rd in 2019, so it's been 2 years now. We flew the Gulfstream 5 aircraft from the National Center of Atmospheric Research, and we did 22 research flights in the boxes that I just mentioned, which amounts to 130 hours of flight. And we dropped 648 dropsondes, which is our main tool of study in this field campaign. And those dropsondes measure temperature, moisture, wind speed, and pressure, and give us an ability to analyze that area, as I will talk more about that. So each one of these dropsondes cost about $1,000. So the plots that I'll be showing you will be the cost of them was about $648,000. So in addition to the dropsondes, we had a hypercloud radar, which is a dual Doppler radar, which we aimed in the nadir position, pointing downwards, to get the cloud reflectivity and vertical particle velocity. And we had other instruments on the aircraft, cloud probes, and all different kinds of measurements that we performed up there. On the ground, we had radio sondes in Santa Cruz and Limon in Costa Rica, on the west and east side of Costa Rica, and in Nuki, Colombia. Now, so Nuki is right here next to our B1A box. And one interesting characteristic of that spot is that it's the rainiest spot on the planet. And so we had the fortune of having some flights in that region when there was convection there. We also had precipitable water networks and rainfall isotope samples that we collected to study origins of the water there. So an interesting point about Nuki, it's a secluded spot on the coast of Colombia. There is no roads coming into it, and our colleagues had some pretty interesting stories to tell us about how they transported the helium for the weather balloons for the daily launches. And they had really big trouble with maintaining the equipment and keeping it dry because of the relative humidity there being just the opposite of New Mexico, being 100% all the time there, compared to us having it mostly 2% most of the time. So this is the aircraft that we use to drop the sondes. These are Sheikha and Dave discussing the flight for that morning. And this is the hypercloud radar that we used in the study. And just to show you an example of convection I'll come to that in just a little bit. So here is how a day would look like on our field campaign. So we would have, we would start our flight in Liberia, Costa Rica, shown here by the white spot. We would fly down, if we were flying B2, to the starting point and do this lawnmower pattern in which we dropped sondes every degree or so. So the reason why we use this pattern, other studies that went to study convection usually tracked clouds and flew around and into them to study the convection. Our approach is sort of orthogonal to that. We wanted to study, to see what the environment is in which the convection forms. And doing this regular pattern gives us the ability to produce a 3D variational analysis to interpolate the data in a physical manner in between, so that we would get the conditions in this whole region. So our group focuses on the conditions of the environment that support convection. And I'll tell you in a little bit what variables we use to quantify those. So here, this was the flight of the first flight, research flight 1, and we had some decaying convection exhibited here by a stratiform convection in the infrared. And this one was B1 flight. We usually flown one of these and then the other because we wanted to capture African easterly waves. They travel about a degree a day, so well, they travel this distance between the boxes in a day. So our idea was to capture those African easterly waves this way. So just as a summary, these are all the drops that we did in this region with the tracks where we've flown. And this one flight, which we called B3 box B3, was a joint flight with NOAA, National Oceanic and Atmospheric Administration. And they had a P3 aircraft flight here to study a precursor to hurricane, tropical storm Evo. We had about 9 tropical storms that happened, initiated in this region during our mission, but we captured about 2 of them in the first mission, and then a mission with the P3 flight. And I'll come back to this area shortly. So just as an example to show you how our clouds look in a decaying and a developing stage, here on the left is the first research flight 1, which I showed you just in the previous plot, where we had decaying convection. And on the right here, we have research flight 20, where we had developing convection here on the bottom. And there is some interesting trivia is that we had to deviate here, and I'll show you in just a bit why we deviated from our flight plan. So here's an example of the hypercloud radar reflectivity, and we can see the flight plan when we flew this way, and we got into stratiform convection, which is exhibited with a lot of reflectivity. Now, in developing convection, like here on the right, we had to fly around it because of lightning activity in the convecting region. So the blue and red represent lightning detection, where blue is within the last 10 minutes and red is in the last 5 minutes. So you can see that it was quite active in that region. So going to the thermodynamic parameters that we studied. So we flew these flights, produced a 3D variational analysis of that region, the fields of temperature, moisture, and wind speed in that box. And we flew up to 15 kilometers. So it gives us a coverage over the whole troposphere. And these are the parameters that we found. The 3 first parameters are the ones that we found to be important in studying convection and the environment in which the convection forms. So first, starting with deep convective inhibition, it is calculated as you take the saturated moist entropy of a threshold layer just above the boundary layer, which is between 1.5 and 2 kilometers, and subtract the boundary layer moist entropy, which is in 0 to 1 kilometers. And this number gives you the stability of the boundary layer in respect to convection. If this number is high, the deep convective inhibition is high. If it's low or negative, around 0, it's less inhibitive to convection. Saturation fraction is it's an important parameter. It's the moisture content of the column. So here it's defined as the mixing ratio of water vapor integrated over the column, divided by the saturated mixing ratio of water vapor in the column. That gives you a number between 0 and 1, or 0 and 100% relative humidity in the column. The third one, instability index, we have found in many instances to be very important for convection. It's defined as the moist entropy from 1 to 3 kilometers, so just above the boundary layer, minus the moist entropy from 5 to 7 kilometers, a little bit higher. And it gives us the low to mid-tropospheric moist convective instability. The lower this number, the more stable the atmosphere, but paradoxically that we found, the stronger the convection and higher the precipitation when this index is low. And I just mentioned the convective available potential energy because we used it. It is a measure used in quantifying the propensity of a parcel to convect further into the atmosphere. And I'll talk a little bit about that in a minute. So these three first parameters are important for the so-called moisture quasi-equilibrium theory that we found in convection in the tropics, and the basic idea of the moisture quasi-equilibrium theory is that the instability index is inversely proportional to saturation fraction, and saturation fraction, being the moisture content of the atmosphere, is directly proportional to the amount of precipitation that falls out of the clouds. And so the convection saturation fraction quantifies the convection. The higher that number, the more clouds you have in that region. So that's an important point. And so we go now and look at the data that we got and look at the moisture quasi-equilibrium theory in our OTRAC field campaign. So here we have saturation fraction versus CAPE, instability index, and DSIN. And the black dots represent East Pacific convective regions. Blue is the Caribbean, and red is the Colombian. So first looking at the CAPE, the reason why CAPE is important because we wanted to look at it because it's used in convective parameterization to predict incidence of convection. And so we want to see how good of a parameter it is for predicting saturation fraction, which is again proportional to precipitation and cloudiness and convection. So we can see that there's a lot of scatter in the CAPE versus saturation fraction. However, when we go to the instability index, we can see there's a much tighter relationship between the instability index and saturation fraction. So the lower the instability index, higher the saturation fraction. So it seems that the instability index is a better predictive factor than CAPE for use in models. And DSIN is sort of also seems to be better performing than CAPE, where we have low values of DSIN, low or negative values of DSIN are associated with higher values of saturation fraction. Okay, so we find that the moisture quasi-equilibrium theory holds in the regions that we flew in, and you can also see that they pretty much, it pretty much follows for all three regions, for all three boxes that we flew in. Next, I'd like to change the topic a little bit, and so we see that the moisture quasi-equilibrium theory holds. We wanted now to see how observations that we use influence models. So as we flew the flights and dropped the sondes, we had a quality check team that quality check the data and send it over to a global assimilation system that models use. They collect the data there and send it to the operational centers, and they assimilate the data. So we had our colleague at the European Center for Medium Range Weather Forecast, and he used their model, operational model, to produce an experiment with dropsondes assimilated and without dropsondes assimilated. So for example, here we have an example of a drop location where we had the zonal wind shown, observations are shown in black. Yes, dropsondes run is shown in red, and blue dropsondes run is shown in blue. And this is an extreme example just to demonstrate how the differences. So when they assimilate the data, you get a much better reproduction of the observations. Now, this difference between observations and the model value, we call a departure. And that's what I'll be focusing on in the next few slides. So just looking at these departures from observations, we want to see how the model performs with and without dropsondes. And here we have, against pressure, has zonal wind, meridional wind, moisture, and temperature. And where, again, the black here is the yes dropsonde run departure, and red is no dropsonde run departure, where the solid line is the mean, and the red and the dotted line is one standard deviation from the mean. So we can see, looking at the, let's look at the zonal wind here, we can see that including the dropsondes, that's the black line, we have a reduction in the error in the mean departure. Ideally, you would have everything be zero, but since this is a modeling venture and other data are used in the modeling, not just our dropsondes, to assimilate. So for example, they use satellite data to simulate when they don't have dropsondes. So inclusion of the dropsondes improves the departure mean and the standard deviation. The standard deviation reduces, meaning that our dropsondes positively influence the model. We see the same thing in the meridional wind. We have the mean is very close to zero, which is what is good, and also the standard deviation has shrunk. When we go to the moisture, there's the moisture seems to be, there's a systematic positive moisture anomaly. So we have, the model is a little bit more moist than reality, than the observations. But again, we have some reduction in this departure when we include the observations. And similarly for temperature. So next thing that we can look at, and we wanted to see, okay, we have this around 700 hectopascals is where we get largest departures in most of the fields. So we can look at the horizontal distribution of these departures. So here we have a horizontal distribution for zonal, meridional wind, moisture, and temperature. And the first row is the yes dropsonde run. The second row is the no dropsonde run. Let's just focus on the wind speed here on the left for panels. If I look at the zonal wind, there, the best is when the departure is small, between -1 and 1, and you can see most of the area have this gray -1 to 1 departure, with some departures going between -3 and 3. So there's some variation in the departures, but it's looking pretty good in both the zonal and meridional wind. However, when we look at the no dropsonde run, the boxes B2, B1A, and B1B, they look pretty good too, even when we don't have observations, dropsondes assimilated, which means that we have pretty good reproduction of the pretty good assimilation from the satellite data. However, when we look at this flight in the box B3, the one where we flew in the precursor of Tropical Storm Evo, we can see that the departures increase drastically. This can be because this is a highly organized system, and maybe the data assimilation really failed there to capture this situation. Now, this is really important because a lot of the studies that have been done before, we fly rarely in the precursors to tropical storms and hurricanes. And this suggests, at least this one flight suggests that it might be really important for us to send more flights into the organized precursors to tropical storms rather than the mature stages, which seem to be well reproduced. So this is the takeaway, that in an organized convection, ECMWF model might be underperforming in data assimilation. Now, looking at the three variables that we found to be important in studying convection, we wanted to see how they are reproduced by ECMWF. So looking at this first panel, I have instability index observations versus the instability index of the yes drop zone run for each of one of those drop locations. And it does a pretty good job in reproducing the instability index and assimilating it. When it comes to DSIN, again, we have observations in the yes drop zone run. There's a little bit of deviation between DSIN and in the model and observations. If you remember, DSIN is in the boundary layer, in the first 0 to about 1.5, 2 kilometers. So this might suggest that the model is underperforming in that region. Looking at the saturation fraction, again, we have a good reproduction between the two. Now here on the right, we have all these fields in the yes drop zone run versus the no drop zone run. They seem to perform pretty similarly in all of them. So that points to the fact that probably the satellite data constrains these fields pretty strongly, and that is sufficient for studying these three fields. As I will show in a bit, the dynamic fields wind is a little bit different story. So let's go to that. So what we can do now is look at these departures that we calculated, integrate them through the whole troposphere, and then normalize them with the pressure difference between the surface and the top. And that gives us sort of a vertically integrated departure. And let me give you an example of these numbers. Here we have on the left the zonal wind, where the black is the observations. Again, this is against pressure, so with height. The red is yes drop zone run. And we can see that they're, like, subjectively, they're pretty well aligned, and there's a good correspondence. Now, when you do the vertical integral, we get a value of about 1.7 meter per second departure. Here on the right, we have another drop, which was, again, in the zonal wind, but which has a larger departure in the upper levels of the atmosphere. And when you do the integral here, this departure, which is basically the surface of the difference between these two lines, goes to about 3.4 meters per second. So you can see that the larger the departure, the larger this vertical departure number. And if we apply this to all of the data for each drop, we get this plot here. So again, the black dots are the yes drop zone run. The red is no drop zone run. And again, for zonal wind and meridional on the top, and moisture and temperature on the bottom, against brightness temperature. So what I wanted to see is if the drop was made in a cloud-free or a cloudy region, how would that influence the assimilation of the data? So if we look at the zonal wind here in the up left corner, any value greater than, let's say, 280 would be a relatively cloud-free region. So you can see that the error, the departure, vertical departure, is very low and clusters in this region of about 1.5 1.5 to 2 meters per second, which we saw in the previous slide, was a pretty good fit. Now, when we look at data that is in a cloudy region, well, let's say anything with brightness temperatures less than 280 Kelvin, we get a lot of scatter, and specifically a lot of scatter and large departures in these red dots, which are the no drop sound runs. So inclusion of the observations of the drop sounds in the model improved the assimilation of the winds. Now the black and red line are just fits to these scatter plots. So you can see that indeed red, no drop sounds, going to drop sounds, we improved the assimilation of zonal wind. And similarly, that goes for the meridional wind. Now the slope of these lines did not change, which probably corresponds to the fact that there's other data assimilated in the model, not just our drop sounds, and they are weighted differently. So maybe if they weighted the drop sounds heavier, we would get change of this slope. But we can see for the zonal wind, for the meridional wind, pardon me, that even the slope is improved. The best would be if it was a flat line. The moisture and temperature, as we might have seen in the three variables that we calculated from these two fields, they're performing really good. So there's not much to say there, except that they're much better than the wind. The reason that this is important is that the African easterly waves that I mentioned before, the field that we use to identify the African easterly waves is vorticity, and it's calculated, the vertical component of vorticity, and it's calculated from the zonal and meridional wind. So any improvement in predictions or assimilation of these two fields can help us better predict African easterly waves incidence in that area. Okay. So we looked now at the departures in this sense, and what I'd like to look at next is the time series of these variables, of the variables that I mentioned before that are important for convective development or our understanding of convective development. So the way that we do this, we isolate convective and non-convective areas. So for example, we use moisture convergence, which is also a proxy for convection, like saturation fraction is. So if the moisture convergence is high, that area is importing moisture, and there's convection happening and precipitation forming there. If the moisture convergence is, let's say, we define here as values less than 0.5, kilowatts per meter squared. I forgot to put the units here. So it's kilowatts per meter squared. This area would be non-convecting because we have moisture convergence. Moisture convergence is small or negative. We include numbers less than 0, which would mean that there's either small import of moisture or export of moisture from that area. So if we take all these, let's say this position here is a moisture convergence greater than 1. We take the daily values, the daily time series of the variables that I show you, and we average them for all the convective points in the region and all the flights. And we also average all the non-convective time series throughout the day for the dry regions, which gives us the following graph. So we have here against time in UTC, the vertical black lines show us the time when we flew. And we have moisture convergence on the top, brightness temperature, saturation fraction, instability index, and descent. So let's first look at the moisture convergence. So we have the moisture convergence increases over time, and just before our flight, we get strong convection forming in our boxes, which we observed. Now, in the dry regions, you can see there's not much moisture convergence, which is to expect because they're dry regions. Okay, one point to note here, which is a big important point about this model, is that there's this moisture convergence peak later in the day, which we do not observe in the satellite imagery. So the model actually invents some convection there, which I'll discuss this a little bit more, but it's a really important point to grasp here. So the brightness temperature for the dry regions was high because there was no cloudiness. And for the convecting region, it started relatively high. And then when the convection started decreasing. This is the way it would develop. You would have less brightness temperature would decrease as the convection decayed. And looking at the saturation fraction, instability index, and DSIN, they obey our moisture quasi-equilibrium theory. We have a decrease of instability index with time and increase of saturation fraction because of processes that I can't really go into right now. And we have DSIN also decreasing. So all these conditions before our flight are conducive to development of convection. Now what happens later, the saturation fraction remains relatively high, so which might have influenced the development of convection in the model in the later in the latter parts of the day. Now this might be the problematic part of the model, that maybe these higher saturation fraction values have induced the model to produce convection, even though it wasn't happening in reality. Okay, so in conclusion, so we studied with OTREC, we wanted to study the convection in the Eastern Pacific region of the planet. And we found that our moisture quasi-equilibrium theory holds in all three regions there, and which results in basically saying that the convection is same no matter what region we look at. However, the conditions which might bring about for that convection to happen are different in these regions. So we're looking into understanding how these different regions, how the environmental factors contribute to development of convection. Second, the model seems to perform well in reproducing and assimilating data in this region and producing our variables that we use to study convection. However, in highly organized conditions, the models might be underperforming in assimilating the data, which might have influence on weather prediction and eventually in climate models. Climate models differ from weather prediction models in some aspects, but they also use convective parameterizations. So we need to improve our convective parameterizations to better model the atmosphere. And as we can see here, there is some area for improvement of prediction of convection in this region of the planet. So thank you very much, and I'd like to invite questions now. Thank you.
All right, thank you, Stipo. Everyone give a round of applause, whether that's, virtually or best way to do. So does anyone have any questions? Or should I ask who wants to ask their question first?
Either
Yeah, I'll ask a question. This is Karthik. So I was trying to, this is not my area of expertise, and really interesting research. I was just curious if you could tie this to the main theme of climate change, and what is it that we're trying to really understand by understanding convection better?
Well, I guess I didn't repeat that point often enough. If our understanding of convection influences the global circulation of the model. So if, for example, our model produces spurious convection in areas where there's no convection in reality, that would probably influence the global circulation and the statistical parameters of the atmosphere in that region, which in turn influences the extratropical region. And although this research doesn't really tie directly to climate change, we're more focused on weather prediction and short-term prediction. I think the parameterizations, which go into global climate models benefit from this research also.
Yeah, I guess let me ask it a different way. So naively, I would think that as the planet warms up, we expect to see more storms likely, and more we see an increased frequency and increased intensity, right? So is the idea that this will allow us to better predict, when storms are going to be forming and which ones are likely to be the ones that most affect people, and so that's where this research is directly applicable. I'm trying to connect the application of your research to.
Absolutely, I think you hit the point, hit the nail on the head there. And specifically, some of the research that I have done for my PhD was looking at organized convection, which is an example, for example, hurricanes. And specifically in this talk that I just gave, that region of the pre-storm convection that was forming there was pretty well organized. And it seems that the model failed in that region. Now, organized convection has been really studied intensely in these last 10 years, and considering how those circulations contribute to the climate change, and as you said, in the intensity, studying the intensity of hurricanes and weather events that come out of that is important. Yeah, so basically it all ties down to organized convection and improving the modeling of organized convection that can benefit models. Yeah.
Okay, one last quick question. So it kind of seems painful to have to do this many flights and get on a plane and study each individual area to understand the physics of what's going on. You did mention at the very beginning that you were trying to use satellite data. So is there a specific satellite amongst the designated observable missions that NASA Earth Science is going to be launching, or anything coming from NOAA that you think will alleviate will give you the information that you need without having to fly a plane?
There's I forgot the name of the satellite that was recently launched from the European Center and from the European side, and they use it to get the winds, the vertical profiles of winds, and they already shown that how much that satellite improves the prediction, and I think they're planning to launch many more of those satellites. So when that happens, we might not have to fly ever again. If we can get accurate wind speeds and good coverage of them, we might be in a really good position for modeling.
Great.
Thank you for your questions.
So this may be a basic question. So how do we expect the models to change, say, as like the Earth's atmosphere warms, or hopefully it wasn't something I missed in the talk.
Well, yeah, I didn't
I
didn't really focus much on that, but yes, we are expecting that hurricanes will increase in intensity and frequency. I'm not sure actually, yes, frequency also. So as the planet warms, we might expect more activity, and especially this last season, for example, 2020, we had quite a few flights into hurricanes. And one of the points of focus of for example, the Hurricane Research Division of NOAA is to study rapid intensification. That is an area where we lack understanding, and flying into precursor events like the tropical storm Evo might be really useful for that. because that's the time when the storms rapidly intensify. So I'm not sure if I answered your question, but
I guess I was wondering, so as I think you did. So as the climate's, changing, we expect all of this to become stronger and
yeah, and more focused. Actually, what we found in our research and what other people are showing, that we might have more intense hurricanes, but very focused. So they wouldn't be as big, possibly, but more focused and maybe even more destructive. I'm not sure if that's a claim I want to make. I haven't seen research claiming that, but from what I've seen, it might be more focused. And also we might have focus of other atmospheric events like droughts. That we might have increased drought frequency with warming. Any other questions?
I guess I'll ask one more question. So what can we do to prepare?
Oh boy, that's
A very open-ended question. Maybe a hard one.
well, I'll invite others to join that question. I haven't really been focused on mitigation. I'm more focused on prediction and improving models for prediction, but adaptation, mitigation, ways to, I'm afraid to say these words out loud, engineering, climate engineering, to understand better what we can do to positively change the climate, might be interesting avenues to pursue.
Yeah, I was going to add, I think that the modeling improvements will, of course, allow us to get advance notice, and so you can prepare for it. So that's one possible, positive thing. But at the end of the day, as sea level rises, and majority of the world population lives around water, and majority of hazardous sites, landfills, refineries, etc., are located in primarily Black and brown neighborhoods. Those are the ones that are mostly at risk. We're going to have to just rethink city planning and where we are living. We already see some of this in Miami, for example. People are moving away from the ocean, but it's just such a monumental challenge that I think rather than address it head on, most of us are just hiding our heads in the sand and not doing anything about it. But I'm hoping that at a local level, places like Annapolis, Norfolk in the US are really starting to pay attention to what the impacts will be, and then changing long-term, like making long-term master plans to account for the changes.
Any other questions? Our next speaker will be joining us shortly, I hope. So we still have more time for questions.
Or discussion, I find.
Yeah, or discussion as well.
What Kartik said was really, I think, I've seen research on how, for example, regions that are like Florida, people started building houses on the waterfront next to the oceans, and when hurricanes and water swells hit, they get flooded. Now, it was interesting that those people lobbied their legislatures to make the insurance companies keep the insurance rates low, so that, for example, people who are inland, who don't have that problem of possibility of flooding when hurricanes hit, they share the costs of the insurance. They have higher insurance rates, so that the people who are experiencing these catastrophes wouldn't have to pay more. So that's kind of an interesting economical, socio-economical interplay of how legislature can help mitigate or plan for these catastrophes that can happen.
It's like I hesitate to ask who's buying the houses on the beachfront.
Well, there's reverse gentrification happening now. So now people are going away from the beachfronts and gentrifying the inland areas in Florida. And so it's pushing sort of the more economically disadvantaged Black and brown communities, into even less desirable areas, further from access to, economic opportunities, city centers, etc. So it's a really good point that you mentioned, Stipo, about the tax things. I had heard that story, but I'd forgotten about it.
Yeah. I guess what you mentioned, that maybe in recent times people have moved. This is maybe 3 or 4 years old story that I know, so it might have changed since everything is changing so fast these days. Information gets old fast. But thank you for bringing that social economical aspect of weather and these changes up. Thank you.
There are some online tools now for looking at, you can put your address in and look at climate risks of a particular property. One of them's flood factor, and the other one I can't remember. It's a little more general in terms of overall climate risk. And there's actually climate scientists on the steering committees for these. So it's it's the best information we have, and I think it'll become a more useful and used tool in terms of the market correcting itself. So.
Oh, thank you for sharing that, Kip. Wrote that down.
Mm-hmm.
Hector, and what did you say was the other one?
I can't remember the name of it off the top of my head. Let me see if I can find it. I did my house, so just to see what the risk factors were. So I'll have to look for the report from that. They'll give you a report on the property you put in there. So.
But do you think, Kip, I have a question for you. So you can know also has a really good tool that shows you, very specifically the sea level rise, and you can change the sea level rise to see the impact. But you mentioned at the very end that somehow the market will correct itself. Like, what gives you that confidence? Because that's historically that's not the case in the history.
Well,
of the
maybe
world.
I'm on the cutting edge of considering these things, but yeah, I mean, I think if people have that information, they're going to, that's going to start to factor into real estate prices. I think that's, and it certainly, you can't rely on strictly individual choices. There's got to be zoning and planning and building and insurance and things of that nature. But the more these tools are available, I think the more people are, once it's like, radon risk in a home, right? That had no traction 20, 30 years ago. And now it's mandatory, right? That if you go and sell a property, you've got to divulge that and other risks. And I think climate, flood risks, that sort of thing are going to become that norm within, another decade or so. So the other one that I found was Climate Check is the name of it. And, there's certainly large uncertainties associated with that, but, I think it's the best information we have at this point. So.
Mm-hmm.
Yeah, there's a company here in Northern Virginia where they're thinking of flying drones and trying to get sort of a few, 1 meter resolution. So you can put in, and then the business model for this small startup is to feed that into insurance companies so that they can better address risk.
Hmm.
I just worry about the disparity it causes, right? Because there's several assumptions here that people have access to the information is given correctly, and so I just sort of feel like it will exacerbate the inequities that we see, and that's what I worry about.
Well, thank you all for the discussion. I think, Henry, my time is up here.
Yes, I didn't want to interrupt the discussion. I don't think we're in a gigantic rush right now, but yes, thank you everyone. And thank you again, Stipo, for being our first talk of the day. I know that can often be one of the roughest ones, or at least my experience is I hate talking first. So our next speaker is, I hope he doesn't mind if I read directly from the bio he submitted to us.
Yeah, that's okay.
Is Dr. Julian Reyes. He is a AAAS Science and Technology Policy Fellow in the Office of Global Change at the U.S. Department of State. And there he leads negotiation issues on gender, climate education, outreach, and training issues at the United Nations Framework Convention on Climate Change, and negotiates on climate science issues at the Intergovernmental Panel on Climate Change and Arctic Council. And he's worked in science society interface and has frequently engaged diverse stakeholders, including university extension professionals, policymakers, farmers, ranchers, and the general public. And he served as the fellow at the USDA Southwest Climate Hub from 2016 to 2019 as well. And he was also a science policy fellow at the U.S. Global Change Research Program in 2014 and a Fulbright Research Scholar in 2011 in Germany. And Julian received his PhD in civil engineering from Washington State University. So, Julian, I will leave the floor to you.
Thanks, Henry. Thanks for that great introduction. And thanks again for this opportunity to speak to you all. I'm really excited to tell you hopefully a story about my experiences in science policy, but also science communication, starting as a graduate student through the past 5 years or so. I received my PhD in 2018, which is not too long ago, but it's been some time. But it was really interesting being a product of the recession. You know, I went into graduate school without really knowing what a PhD was. As a first generation college student, my parents, just got their AAs and they didn't really know what a bachelor's degree was or a PhD. And so I was really fortunate to engage in a lot of diverse opportunities that explored ways to engage with stakeholders and really reach outside of the ivory tower, outside academia, and really explore what I could do as a scientist outside the university system, which to me was amazing to see all these PhDs doing great things. And so I just want to start with a disclaimer that the views expressed here are my views only, and as a AAAS Science Policy Fellow in my personal capacity, they do not necessarily represent the U.S. Department of State or its policies or those of the U.S. government. And I do hope the goal of my presentation is to highlight opportunities for graduate students and early career scientists to really engage with decision makers and the general public and really demonstrate the value that scientists and engineers can contribute to the policy making and implementation process. And I think you all can see the next slide. So I grew up in the Seattle area, very much a city kid. And then I ventured off into Eastern Washington here on the picture in the top right, which are the rolling hills of Palouse, very rural college town, around 20,000 people, including the university, which was around 15 to 18,000 students. And so very big difference, but that really shaped the way I think about communicating with people. You can imagine talking about climate change, for example, is very different in an urban area versus a rural area. You can think about talking to farmers. Their bottom line is very different than the bottom line, let's say my family, in the Seattle area. But I truly enjoyed my time at Washington State University, where I received my bachelor's degree in civil engineering and PhD. And I was fortunate during my undergraduate time and graduate to actually visit Germany twice, first as German Academic Exchange Service intern, and then second as a Fulbright Scholar, as Henry mentioned. And so that kind of shaped how I started to thinking about how I talk to people. Having these various perspectives is really important to me. And during my PhD, I did a lot of work in ecosystem modeling, so very computational, like really no connection to the real world unless I was looking for data to help evaluate my model. And so as a graduate student, I started asking myself, so what is the purpose of my research? Why am I doing this? And so I started out, seeking opportunities to learn how to explain the societal relevance of my research, but also find a deeper meaning in what I could do for society as a whole. and then, really how PhD scientists were helping communities adapt to climate change. And so, I found opportunities to explain to a rancher. I visited a rancher in Spokane, so just an hour north of Pullman, Washington, trying to explain like what my ecosystem model was, how it may be useful to him in his ranching enterprise. That was one example of how I was trying to communicate my research to someone. I also started exploring ways to talk about my complex research to different broad audiences. So on this bottom right, bottom left picture, you can see me engaging with folks at the Union of Concerned Scientists, and I end up writing a blog for them talking about, where my interest in science started from, and then trying to explain my research to a very broad audience. Then this picture on the bottom right shows me at the American Geophysical Union conference, and this was a session on community science, or how do we link scientists with community members, and what does it mean to be a listener first, and then engaging with communities and trying to help them and help them with their needs. And so during graduate school, I mentioned I was fortunate to be a part of an NSF-funded interdisciplinary graduate program called an IGERT. It allowed me a 3-month science policy fellowship at the US Global Change Research Program. And that was a really great opportunity for me to move to DC for a summer and really engage in science policy. In the US Global Change Research Program, it coordinates climate research and investments among 13 federal agencies. It's also responsible for the National Climate Assessment, as you may be aware, which is mandated by Congress. And so, one of my first, suggestions, if you are interested in science policy as a graduate student, is to seek out ways to engage in science policy, whether it's through a fellowship or a short experience. That'd be my first suggestion. And it doesn't have to be, in DC. I think the pandemic has showed that we can do a lot of our work virtually. And so if there are virtual ways for you to intern or be a fellow, I think you should definitely seek out those opportunities. And again, whether at the federal, national, or state level. Another piece of advice I would say is to take non-STEM courses. And so as an engineer, I took a lot of, math and engineering courses, but I actually ended up taking, I think almost half of my graduate courses were actually non-STEM. I ended up taking a public policy course on how science policy works. I also took a philosophy of science, climate change science course, which is very different. It's thinking about how people think about science. So that was very different. That allowed me to engage with non-engineers, non-scientists to talk about climate change. And you would think we would be able to talk about it, but really it took us some time to develop the same language, because you can imagine, an economist will talk about climate change very differently versus a philosopher versus a political scientist. And so I would say if you have the opportunity, I know you're all busy with your research and you're wanting to be done with your courses, if you have an opportunity, it's a really great chance to be able to contextualize what you're doing, broader than just science, technology, engineering, math, and really engage with others outside your discipline. Something else, I was able and fortunate again to attend and participate in interdisciplinary scientific conferences. So I mentioned the American Geophysical Union is my main scientific conference, but since I did a lot of ecosystem work, I also attended the Ecological Society of America as one example, and that is very different, very, I don't want to say not hard sciences, but less engineering, of course. And that was also a great opportunity to engage with those outside my discipline, try to explain my work to those who have no idea, what hydrology may be or what kind of model I was using. And related to the second piece of advice, you can also think about attending conferences you've never thought about. I attended the Western Political Science Association conference, very different. I was like one of 5 scientists that attended out of 300, very weird, but it was a great experience, very different. They don't do PowerPoint, they produce papers and they present their papers like in a defense and they defend their ideas. So that was a cool experience, but again, a great way to think about how to explain your research or science to a non-technical or a different discipline. Another advice, get involved in student advocacy, such as through the Graduate Student Association. And there are all sorts of ways to, not only get experience in, explaining your science, but it also could be just engaging with your colleagues or, fellow graduate students. And that also can help you in your future career when it's engaging with different personalities, for example, or trying to advocate for an idea. So I think that's also a great place to seek out science communication and science policy opportunities. And related to all of these, you can really write about your science to diverse audiences. So again, like a blog post, for example, or even on Twitter, for example. I mean, how do you fit what you do in 280 characters? That's really hard, but it's possible. And so if you're able to do that, that's a sign that maybe, science communication, science policy is really an avenue for you. And finally, one of the main pieces of advice that'll come through my presentation is to listen first and ask what communities need and want. I think it's hard for scientists to just kind of sit there, right? Because we've done all this great research, we've done our time to get our PhDs. But it is really hard if we're working with, on the ground communities, to sit and listen. But that's really important when we're trying to help them. And we really need to figure out, what is it that they need versus us talking at them and giving them information that may be not really necessary. And so I'll go through kind of my circuitous journey in science policy, how I ended up from A to B. And I'll first talk about what is science policy, very brief foundation, and how do you engage with decision makers. And then second, I'll go through how do we talk about climate with farmers and ranchers. And some of you may recognize this picture. I was a fellow in the Southwest Climate Hub in Las Cruces, New Mexico, so 3 hours south. So these are the Organ Mountains. I still miss Southern New Mexico a lot. And finally, I'll talk about my current work in international negotiations and climate change, and then we'll end there. And so, you're going to ask, what is science policy? I tried Googling this too, and it's really the impossible question. That's kind of the answer I found. And for me, it's hard to explain. But I found this funny quote from a blog that's a vague combination of science writing, communication, advocacy. And that kind of makes sense given how I described kind of what I was able to do during my graduate studies and what I do now. And a lot of the people who work in science policy really take what is happening on the bench and bring it to the light of day. So we do a lot of synthesizing. We are looking at news articles, journal articles, and really taking the most important and relevant bits and bringing it up to our principals so that they can understand what is it that's important about this stuff. And essentially we serve as a bridge between researchers and the public. And so like I said, we're trying to synthesize and translate that information into something that we can package to other people so that they can use that in their decision making. And then again, a few figures on what is science policy. On the left, you can think about it as engagement. How do we bring out evidence? And then, it's a mixture of outreach. I like this other figure on the right showing different career paths in science policy, whether it's in advocacy, such as with the Union of Concerned Scientists, science communication, diplomacy, working at the State Department, what does that mean? It can also still mean data analysis and data visualization if it supports decisions, related to science policy. And then you can see a variety of other paths, including regulatory efforts and policy implementation and program management. And then moving on, talking about how we engage with decision makers and communities. I like this figure that shows that there's a continuum of engagement. You can have no engagement with scientists, that's fine. Or you can get up to collegial, which is a type of continuous engagement where you're actually incorporating local needs and knowledge with research. And so, engagement with communities doesn't have to be one or the other, no or yes, but it can be in the middle, or like such as a consultant where it's more of a one way where the community has a need, you respond and that's it. But, I think getting towards collegial would be kind of the best way to get the co-production of knowledge and research. And then in this kind of on the far right, consultant, collaborative, and collegial, you have boundary organizations. And they sort of convene, translate, collaborate, and mediate. And so you can see these three organizations at the bottom. The first I'll talk about the USDA Climate Hubs. There's also the NOAA RESA program, so the Regional Integrated Sciences and Assessments program, and also there's programs through USGS, through DOI called the Climate Adaptation Science Centers, or CASCs. And so these three organizations work together, obviously, but they do a great job of working together and convening workshops or meetings to really understand what stakeholders need on the ground and get those climate-informed resources to them so that they can make better decisions. And they also translate research in a way that stakeholders can understand. They collaborate. And they may mediate various issues related to climate on the ground or up to the federal agencies. And then one way that folks in science policy do what they do is through science communication. And so I took these bullets from, it's called a handbook for IPCC authors. And I really like the way that they laid it out, talk about the real world when you're talking with people, connect with what matters. So for example, if you're talking with a rancher, I don't think they're going to care about IPCC. What they're going to care about is, do I have enough forage for next season? How does it impact my bottom line? Do I have enough money to support my livelihood? Tell a human story, start off with what you know, and then use effective visuals. And then this last part, they had put be a confident communicator, but I would argue you should be an effective listener. Especially in DC, a lot of people talk, not a lot of people listen. I think listening is something that's a unique thing to have. And then this other figure, which I like from AAAS, shows typically how researchers write or talk. You know, they start with a lot of background, which I'm also doing, unfortunately, and then you get to the conclusions at the end. But for the public, they just want to know what the bottom line is, the so what, and then supporting details later. And I'm sure you've all seen this figure, but I thought it was another way to summarize what I meant about science communication. So now I'll go through two examples of kind of my science policy journey. And as I mentioned, these two stories show kind of the balancing act between using science for society and trying to make sure you're doing the work that needs to be done. The first is at the local, state, and regional scale, working with the USDA Climate Hubs program, where we work with farmers and ranchers to enhance their decision-making and try to infuse some climate-informed decision-making, that is. And the second one would be my current work on the international scale, working at the US Department of State, supporting international climate negotiations, coordinating climate science, and formulating climate policy. And so a little bit of background about the USDA Climate Hubs. There are 10 hubs around the country, shown in this figure on the right. Our mission is to develop and deliver science-based region-specific information and technologies so that farmers, ranchers, extension, universities, and other USDA agencies are empowered to make climate-informed decisions. And so you can see on the bottom the list of various USDA agencies that we work with, including the Agricultural Research Service, the in-house research service for USDA, the Natural Resources Conservation Service, NRCS, US Forest Service, APHIS, the Farm Service Agency, and the Risk Management Agency, RMA. And so some of you may know or be familiar with many of these agencies, which a lot of them are based, there are a lot of them in New Mexico. The Climate Hubs program is really trying to address the impacts of climate change on working lands. And the program does this by connecting USDA research agencies to program agencies to really build resilience to a changing climate. And as I mentioned, I worked at the Southwest Climate Hub located in Las Cruces, New Mexico, and we were based out of an ARS, Agricultural Research Service unit at the Jornada Experimental Range. And then Southwest Hub covered a very large region, actually, Nevada, Utah, Arizona, New Mexico, and the Hawaiian Islands, interestingly enough. This is a complicated figure, but I like it because it looks at the co-production cycle, essentially taking all these various actors who the USDA Climate Hubs should and do work with, including extension, the agencies and federal partners in the green boxes, and kind of showing how do we actually do what we say we want to do. So the hubs were essentially established to improve information flow to stakeholders by translating science into useful tools and products, and improve the information flow from stakeholders to provide feedback to research agencies. So again, that two-way interaction, and then this is done through co-production. So another way to define co-production, especially in the context of sustainability, is an iterative and collaborative process involving diverse types of expertise, knowledge, and actors to produce context-specific knowledge and pathways towards a sustainable future. And so you can see the various actors involved, not only in the green, but also states, private sector partners, on the far left, NGOs and nonprofits. And of course, this process is one that you refine and review over time. And you can imagine with this large co-production cycle and many stakeholders that the process can get unwieldy. And I would argue that one of the major challenges in this was trying to make everyone happy. You can imagine, for example, I was working at an ARS facilities and that they are who paid me, but yet we still want to bring value to our other USDA agencies. But yet you still want to make your ultimate stakeholders, your farmers and ranchers, the USDA customers happy. And so it is really difficult trying to make everyone happy, but I think it's important to realize that your bottom line is to help farmers and ranchers and really help them adapt to a changing climate. And through that process, you become really good at providing the right context to do your work and really showing added value to all the various partners involved in the process. And so the climate hubs have three strategic objectives. There's science synthesis and assessment, and that's essentially providing periodic regional assessments of risk and vulnerability to various sectors and rural economies. And this includes writing portions or contributing to the national climate assessment through the US Global Change Research Program, as I mentioned. And through the science synthesis and assessment, we also work closely with extension organizations, universities, the private sector to be a source of user-friendly and information developed from a wide variety of sources. The second objective is technology transfer and tool development, and that is essentially delivering science-based agriculture, forestry, and land management tools and strategies for responding to impacts with changing climate. And that includes drought, extreme weather events, and changing growing seasons. Really improving access to useful and usable regional data and climate change projections and forecasts really help support our risk management and climate adaptation planning and tools. And finally, outreach and education. So this involves providing outreach and education to farmers, ranchers, forest landowners on science-based risk management. This also includes educating natural and agricultural resource managers on the latest understanding of climate science and the effects of climate change on working lands. And so again, that kind of translation role, packaging what's happening, in the IPCC reports or National Climate Assessment in a way that other folks can understand, so that it's not so technical, or that you're actually giving them the pieces of information they need. And so I'll go through one specific example. So as part of the Climate Hub's mission to deliver science-based region-specific knowledge to farmers, ranchers, and landowners, we embarked on a collaborative project between the Risk Management Agency and the Agricultural Research Service. And this was a multi-pronged approach to achieving our ultimate goal, which was essentially understanding the role of long-term climate trends and crop insurance data to support sustainable agricultural production and community resilience. So a bit of background, the federal crop insurance program through the USDA Risk Management Agency provides a financial safety net to farmers and ranchers to mitigate against crop losses due to natural perils or declines in price. And I don't remember the latest data, but I know back in 2016, the RMA had insured over 100 billion, that's B with $1 billion worth of crops just in 2016 alone. I think that continues to increase. So a parallel program could be the federal flood insurance program. So the federal government plays a role here because it is difficult for private insurers to really do what RMA does. And not to say there aren't private insurers in the market, there are, but that the USC RMA provides a significant portion of the insurance payouts to farmers and ranchers. And so with these data, we really saw a great opportunity, long-term data of crop losses at fine spatiotemporal resolution. So, me as I was starting off, coming out of graduate school, got my PhD, I was like, what can we do with these data? And it was long-term, starting in 1989 to now. I'm like, what can we do with these? And it was at the county level, and it was at the monthly time step, and we were able to parse out various causes of loss, such as drought, heat, hail, cold, wet weather events. So I started asking questions like, well, can we see, are there any climate trends? Are there more drought losses over time, or are some of these heat losses related to El Nino, or who knows what? And so I started asking these questions. And this was really a place for the climate hubs to play a role. And since we were all about synthesizing existing data, research in the agencies, breaking down data silos, unfortunately, it was for me, it was a great project for 3.5 years. That was incomplete because I had to I went to a new position, but really a lot of my time was spent really breaking down data silos, trying to get folks to give me what I needed. But even as a USDA employee, it was quite difficult, to be honest. And then in addition to breaking down data silos, we also we tried to ensure that the data that we were working with were useful and usable. And I'll get into that later. And so, as I mentioned, we had 3 specific objectives. And so we were trying to understand the role of long-term climate trends. Second, we also tried to analyze the crop insurance trend over time to see if there were any, specific regional trends we were seeing. And finally, we wanted to develop a platform to easily access RMA data, which I'll show you later. The way I access the data were basically large CSV files, which are not very helpful. So let's say a farmer or rancher, they're not going to download megabytes or gigabytes of CSV files and do an analysis. That's not what they're going to do. And so we were trying to bridge that gap. And in addition, we were also making sure that the data made sense. And, that took lots of years, actually, to be honest. And then this figure on the right shows kind of what came out of this first objective in understanding the crop insurance trends. So here we examined the top 10 weather and climate related causes of loss by region from 2001 to 2016. And the increasing bubble sizes indicate a larger contribution of that reported cause of loss out of total payouts to farmers. So when a farmer, he gets insurance, and if there's something that happens to his crops, his or her crops, he gets a payout or an indemnity. And that's what we were using to measure these values from the size of the bubbles. So it's no surprise to see drought in the orange as an excess rainfall in the purple as the top two causes of crop loss. They comprise almost 71% of national payments, but it is interesting to see how the size of the bubbles nationally compare regionally. And you would expect that, as there are different, obviously, climates across the country, but also, farmers will plant things differently across the country. But, this begins to paint a very different picture of each region's unique climate, management, and stakeholder needs. And so in terms of this, the second specific objective, we wanted to analyze crop insurance payment data. In this example, we looked at payment data over counties in the Ogallala Aquifer, and we worked with partners in the region. So here I worked closely with the Ogallala Water Coordinated Agriculture Project, or CAP, a USDA NIFA funded project to help scope, analyze, and interpret these data from our ultimate published paper. More importantly, we use these data to empower farmers, ranchers, extension officials, and others to really examine these long-term data and how these trends can provide additional context to their shorter-term decision-making. And the crop insurance loss data can really help integrate long-term trends with near-term management practices. And it was interesting, in this research, we found that drought, hail, and heat were the leading causes of crop loss for the region, no surprise there. But we also found that northern counties of the Ogallala, so in Nebraska, may actually perceive hail as a greater risk and actually may be better equipped to handle drought losses as compared to the southern Ogallala. And so in panel C, you can see the darker purple indicating a larger percent of indemnities in that county as hail. But we also saw that perhaps those counties in the north may actually be hedging their bets with hail, essentially insuring their crops when they may not need to. And so we also thought that was an interesting finding. And we also thought that these findings could also potentially change some policy, perhaps changes in crop insurance policy in terms of what folks are buying in specific areas so that they aren't necessarily hedging, they can save money, or targeted adaptations. So in areas of larger indemnities related to drought, you can potentially target a better crop insurance program for those producers. And finally, we have the agri sphere, which was really the third objective, which was to increase accessibility, discoverability, and usability of long-term crop insurance data for climate-informed decision-making. And so it's through this portal, which you can just Google, that you can actually access the crop insurance data, I think from 1989 through 2018 or 2019. And again, as I previously mentioned, these data were previously just a bunch of CSV files. And even through conversations with the USDA RMA, they have not made those data available in any other way. And so we are the only folks who have made these data available for anyone to use. It's also, so it's a web-based platform, it's a website obviously, but you can also do some simple analyses looking at monthly trends, yearly trends. You can look at specific causes of loss by crops. You can see what affects cotton most in Texas, or you can see what affects pecans most in New Mexico versus Georgia. And while you may think that, it might be interesting to look at those data through the lens of crop insurance data. And again, we hope that that type of analysis provides a different lens to the management that these folks are doing on the ground. And finally, as an anecdote, in terms of if folks are actually using this tool, right? So a lot of people will develop tools, but they never look at or evaluate whether folks are using it. So not a formal evaluation, but we had anecdotes that people were actually using this tool, and that I would get direct messages on Twitter because the site was down. They couldn't get data for their class to use. Okay, so we knew folks were using the tool, great. I also heard from a drought czar in Washington State that they were looking at past trends to see whether they would recommend to the governor of announcing a drought declaration, and especially in agricultural areas. And so it was nice to hear people are actually using the tool. And unfortunately, given the amount of time I had and the financial support, we just couldn't do a proper evaluation. So that's part of another challenge in terms of doing a lot of this work and working with communities and stakeholders. Finally, just to show a brief example of some stakeholder outreach and education. We provide outreach and education to farmers, ranchers, and forest landowners on science-based risk management. We engage with them to help lower adaptation barriers, manage risk, and enhance rural productivity, and really provide opportunities for scientists, decision makers, and communities to engage with one another. The figure on the bottom right shows that last bullet point. We convened a session at the American Geophysical Union called Science to Action, and really providing a platform for scientists to talk about the great work they were doing with communities. And the top right shows a picture of a former colleague, our tribal coordinator, Helena Deswood, and she's talking at the quarterly ranchers meeting back in July 2018 at Fort Defiance, Arizona. So some quick lessons learned. First, meet them, the stakeholders, where they are, not where you want them to be. Listen first and lead with what's important to them, to stakeholders. The loading dock approach to linking science to action to decision making should really be minimized or avoided. So the loading dock approach assumes action can be driven by science transfer only or providing more science or knowledge. And so that just assumes that I can just give you more knowledge and that'll help you. And we know that's false. Even through our work with the climate hubs, we know that that's not what folks want. And finally, we are better together. Climate networks should and do work together. As I mentioned, there are the hubs, the NOAA RISAs, and the CASCs. And in our work on the ground, we never step on anyone's toes. We were asked various questions through our various channels. And if anything, we enhanced the work that needed to be done on the landscape. And from my first experience working on the ground, I'll leave you with this really fun quote. Sit down, shut up, and listen. And that's really hard for scientists to do, as I mentioned, just because they have a lot of great information they want to tell you, including myself right now. But that is hard when you're working with communities. But I think, as I mentioned, if you remember to listen first, and actually Gina McCarthy said that very recently on a climate justice symposium yesterday, I think it'll serve you really well if you're working with communities and stakeholders on the ground. Okay, so now I'll get to my second experience at the US Department of State. So the US Department of State leads America's foreign policy through diplomacy, advocacy, and assistance by advancing the interests of the American people, their safety, and economic prosperity. And so you may ask, okay, why are there scientists at State Department? What is science diplomacy? So science diplomacy is really the use of scientific collaboration among nations to address common problems. So an example would be climate change and now COVID. Those are global and they know no boundaries. And science itself is a distributed global enterprise that can be replicated, verified, and inspired. And so, through the work at the State Department, we can take what's happening in the US and, we could apply that in other countries or show them that this is a real success and that it would be a great example for them. So for example, the USDA climate hubs might be a great example in Mexico, for example, if they're really trying to reach, agricultural stakeholders, for example. And these articles shown about from the Hill showing, recent articles showing the State Department needing more scientists, upping science diplomacy. And so there's a really big need for scientists in all sorts of places in the federal government, but even more so at the State Department. Where I work, so I work in the Office of Global Change. That's within the Bureau of Oceans and International Environmental and Scientific Affairs. It's a really long name. We just call it OES, Oceans, Environment, and Science. And OES was actually created in 1974 by Congress in recognition of diplomatic and economic importance of handling different scientific issues in a global manner. And the Office of Global Change is responsible for implementing and managing US international policy on climate change, and also representing the US in various negotiations under the UN Framework Convention on Climate Change, or UNFCCC, and other climate-related international fora. And we work closely since January with the Special Presidential Envoy, so SPEC, John Kerry's office. And so you can see these two articles that were talking about how John Kerry's office would work and what he would be doing. And so we get a lot of our political guidance and a lot of our advice from SPEC. And in the past, we would have to go through regular US Department of State channels, but now that we have a political who works on international climate change, we go through John Kerry's team to get the things done that we need to. And you may also ask, well, what do you actually do at State? So we do a variety of different things. We provide climate science expertise, which I'll get into. We negotiate on international treaties and documents and multilateral fora. And when I say negotiate, that means we ensure that language in reports or resolutions adheres to US foreign policy and is scientifically accurate. And we can also manage and lead various international programs. And finally, we also coordinate interagency and international efforts. So now I'll go into the UNFCCC and Paris Agreement, just a bit of background. The UNFCCC is the International Environmental Treaty that addresses climate change. The ultimate objective of the convention is to stabilize greenhouse gas concentrations at a level that would prevent dangerous anthropogenic human-induced interference with the climate system. The Paris Agreement ramps that up. The goal is to limit global warming to well below 2 degrees Celsius, preferably 1.5 degrees Celsius compared to pre-industrial levels. And then, despite the former administration's intent and official withdrawal from the Paris Agreement, the US remained a party to the UNFCCC. And so that's why our office still exists and why we're still doing work. We still existed as a party to UNFCCC. And so as mandated, we continue to participate in those negotiations. And as you all are aware, the United States is officially a party to the Paris Agreement again as of February 19th, 2021. And then this last bullet point about COP26. So COP is the Conference of Parties, and it's attended by all the countries that signed the UNFCCC. Again, the treaty agreed to in 1994. And the big COP meeting that's scheduled for this year is in 2021 in Glasgow. And the hope for COP26 is to continue to increase climate ambition to ramp up countries' goals to reach net zero or to really implement the goal of the Paris Agreement. The last COP, as you can see on COP25, there were a lot of unfinished business. And so if you can see the news, there's a lot of people wanting more ambition and more saying that work needs to be done by COP26, which is very true. But it remains to be seen how COP26 will look given the pandemic, and a lot of our work is virtual. And so we'll see what happens in November 21. And so a little bit about the Paris Agreement. As part of that, there are nationally determined contributions, or NDCs. And those are really just the plans and actions by countries to reach the goals of the Paris Agreement. There's various sources of support, including finance, technology, capacity building. And there's also information on how we track progress. How are we making progress towards the Paris Agreement goal? And that includes transparency framework and the global stocktake. The global stocktake is assessing and taking stock of our work. And then here, I didn't want to read all this, but some of the most recent news and interesting policies related to climate change, if you're interested. As you all are aware of, there was the latest executive order on tackling the climate crisis at home and abroad. And this is where we get a lot of our talking points, such as, the climate crisis is at the center of US foreign policy and national security considerations. They're taking a whole of government approach to the climate crisis. We are enhancing global ambition. So on April 22nd, Earth Day, and April 23rd, President Biden is hosting the Leaders Summit on Climate, and John Kerry's office and our office has been working very hard on that. And finally, on the domestic side, there's the National Climate Task Force, which is led by Gina McCarthy and with the heads of the other agencies. And so a little bit about the work I do now to make the story to connect. I work on a variety of different climate policy issues. I work on gender and climate education and outreach for the UNFCCC and Paris Agreement. I also work on international climate science through the IPCC, the Intergovernmental Panel on Climate Change. I also work on Arctic Council issues with this expert group on black carbon and methane. And finally, I also work on a region called the Western Hemisphere. And so that's basically all the countries in the Western Hemisphere, which is quite a lot. And then I will go through the first 3 bullets to kind of show what I do on a daily, weekly basis. So under gender is important in the UNFCCC, and really to recognize the importance of a gender balance and recognize gender in the various processes, different development and implementation of national climate policies to make them gender responsive. And under that, we have a gender action plan that really is to advance knowledge and understand gender responsive climate action and mainstream the implementation of the UNFCCC and Paris Agreement goals. And so part of that involved this virtual workshop this past summer, where we looked at different ways that folks could integrate gender into national climate actions and featured various countries showing their successes and challenges in doing so. Another thing I do at the UNFCCC is something called Climate Action for Climate Empowerment, or ACE. And that involves 6 different elements. You see this figure in the top right, which is education, training, public awareness, public participation, public access to information, and international cooperation. So that's a lot of different things, but really it's about empowering folks to really be able to talk about climate change in a way that is useful and usable. And part of that ACE work includes negotiations. So that's implementation of both UNFCCC and Paris Agreement through ACE. That includes a source of dialogue, so promoting exchange of best practices and lessons learned among the various nations. A series of workshops and events to really strengthen the network of those involved in ACE, but also capacities of ACE focal points. And these ACE focal points are nominated by each country. And their goal, and what they do is they try to integrate what's happening on the domestic side related to ACE and kind of get them up at the international scale to discuss and share with other focal points from other countries. And finally, related to ACE, it's really about empowering youth to take climate action. On the climate science side, so I work on IPCC issues. A little bit about IPCC. It was established in 1988 under UNEP and the WMO, the World Meteorological Organization, really to assess the latest climate change science. There are 3 working group reports and a synthesis report. Working group 1 focuses on the biophysical science. Working group 2 focuses on adaptation and impacts, while working group 3 focuses on mitigation. And through these processes of writing the reports and approving, thousands of experts contribute as authors, reviewers, and government representatives. And the review process really ensures the highest quality and scientifically robust reports. And as part of my work at the in the Office of Global Change, we help with the interagency review, and we really that's our number one goal, is to ensure the reports are reviewed carefully so that it's the highest quality report, because these are the preeminent comprehensive reports on climate change science. I will also note the summary for policymakers for the working group reports are also a very big undertaking by both governments and experts, and they're actually negotiated line by line. So that's why it's called the Intergovernmental Panel, and that when we negotiate the summary for policymakers, in the room, not only are there scientific experts, but are also government officials. And so you can imagine a whole week sitting in a very large room, such as here in the bottom right, and you're going word by word through 30 to 50 pages of a summary for policymakers for a climate change report. And any country can say they want to change, and there are over 195 nations represented. So you can imagine it's a very huge task. But we're currently in the 6th assessment cycle, so this has happened 5 times, and so we're currently in the 6th, and so the process has worked. So the IPCC also meets as a panel. So again, the panel is of 195 member countries. The panel works by consensus. And the panel will meet to discuss the organization's budget and work program, the scope and outline of reports, issues and the principles and procedures of the IPCC, so how we actually work, and then the structure and mandate of various working groups and task forces. So as I mentioned, one example of the work they do is to negotiate line by line a summary for policymakers. But interestingly enough, the last time we were able to travel for an IPCC event was back in February, end of February, in Paris, France. And I still remember that trip vividly, since it was right before the city shut down, and folks weren't really sure what this coronavirus thing was. So it was pretty scary. But we spent a whole week negotiating these 2 pages of bullets, which was the proposed outline of the 6th assessment synthesis report. And so here you have a variety of scientists and government officials arguing over various bullets of how an outline will be structured for a synthesis report. And so you can imagine it's a mix of both science, but also making sure that your own country's foreign policy is represented in here. And so this is approved, obviously, but it literally took a week and some really late night meetings, from 1 a.m. to 3 a.m. to get a consensus. And that can be hard sometimes. There's a lot of give and take. Something else I worked on with IPCC was a gender policy. I was really proud of this, one of my first assignments. And so this policy really mainstreams gender in IPCC's work to make sure we consider gender in an inclusive and respectful manner, and make sure there's balance and participation and equal opportunity for all. And so in the climate change office, I had to work with NOAA, our lawyers, our other office on the Global Women's Initiative, and the IPCC Gender Task Force. And so it was me trying to integrate all these various perspectives and views, and ultimately what is presented to the panel is the IPCC Gender Policy and Implementation Plan, but it still needs to be approved by over 195 nations. And so it was ultimately approved, which I thought was a really great accomplishment, especially given the past administration's stance on gender equality. And so we were able to get a definition that was agreeable to all nations. Just some quick IPCC updates. As I mentioned, we're in the 6th assessment cycle, and really it's been unprecedented in terms of the amount of work, but also pandemic challenges. So far, 3 special reports have been published: global warming on 1.5, climate change in land and oceans and cryosphere and a changing climate. As I mentioned, Working Group 1, Working Group 2, Working Group 3, and the synthesis report will soon be coming out in the next 1 to 2 years. I know we're running out of time, but the importance of climate science for policy, just quickly to say here, is that I don't know if you've seen or heard Secretary talk, but he consistently uses the phrase, keep a 1.5 degrees Celsius limit on temperature rise within reach. And that is used to help ramp up global ambition. And so that 1.5 degrees Celsius, that phrase is from the 1.5 special report I mentioned. And so the administration, Secretary Kerry, is really pushing for net zero greenhouse gases emissions by 2050 or before, which is based off of that scientific report. I'll quickly jump into my work on the Arctic Council. Very different. The Arctic Council is the leading intergovernmental forum promoting cooperation, coordination, and interaction among Arctic states, Arctic indigenous peoples, and other Arctic inhabitants. And the Arctic states are Canada, Denmark, Finland, Iceland, Norway, Russia, Sweden, and the United States. And the Council's activities are conducted in these various working groups on the right, including an expert group on black carbon and methane, which I'll get into. And so, as you may know, black carbon and methane are short-lived climate forcers that contribute to climate change. This group, this EGBCM, was created to review, analyze, and assess progress toward reducing black carbon and methane. And our office represents the US on the expert group and provides both scientific expertise and we negotiate acceptable policy. And an interesting story about this group is that we are supposed to submit a biennial report on our black carbon and methane emissions. So you can see in the bottom right, this report to the Arctic Council in March 2021, so submitted very recently. But this report was actually not approved to be submitted in the former administration, and that was quite difficult. But given the new administration and their stance on being as ambitious as possible, we decided the report should be submitted. There was nothing, it was just numbers on black carbon and methane, and we wanted to showcase what we were currently doing to reduce those. And there's a summary report that is published from all the various national reports that are published called the Summary of Progress and Recommendations. And we're currently about to wrap that up. So Summary of Progress and Recommendations for 2021. And that will be approved at the May ministerial, where hopefully the Secretary of State or Secretary Kerry will be in attendance. Okay, just in time. Finally, I wanted to talk about how I was afforded this opportunity to work at the State Department. So another opportunity for, if you're close to finishing up your PhD or you're an early career scientist, the AAAS Science Technology Policy Fellowship. It's an opportunity for scientists and engineers to learn firsthand about policymaking. You serve 1 to 2 years across the executive branch in various federal agencies or in congressional offices. It's really a transformative career opportunity. You can use it as a pivot, if anything. And really the STPF network is really powerful and well respected for us in both government, industry, academia, and nonprofit. Especially here in DC, if you say you're a AAAS fellow, I would say 95% of folks know what that means. And outside the Beltway, obviously the language is quite different, but AAAS Science Technology Policy Fellowship is very highly regarded. And quickly, just to discuss, where fellows are placed, this figure shows the variety of agencies from agriculture to defense to energy, Homeland Security, State Department, USAID. And so in the last decade, 2013 peaked with over 282 fellows, and then 2019 tied with 2014 as the second highest number of placements with 268 fellows in each of those years. And then since 2019, state, National Institutes of Health, NSF, and the Department of Defense have been the top agencies hosting most fellows. And then there was a recent study on looking at where fellows go. So, they found that the STPF really had a significant impact on the career trajectory. So I think the number of surveys, I think they surveyed 1,200, almost 1,300 alumni to see, where they were before and after the fellowship. So for example, here, folks, a little under half of the folks came from academia, and just after the fellowship, they ended up getting a government position, so this orange. And then even just after the fellowship to currently, a lot of them are still in government. A lot of them did go back to academia, but you can see a lot of them ended up staying in government. And so if you're thinking about a position in government and maybe you as a scientist, you want to formulate policy, AAA Science Technology Policy Fellowship Program could be for you. Okay, and then some other science policy opportunities. There's a NOAA Sea Grant Canals Fellowship, and so that's for grad students, current grad students interested in oceans, coastal or Great Lakes resources and policy. There's a program through DOE in the Energy Efficiency and Renewable Energy Science Technology Policy Program. There's also the Presidential Management Fellowship Program, PMF. And finally, if you are part of a scientific society like AGU, AIP, the American Physical Society, they probably do sponsor a fellowship of some sort in the science policy realm. So finally, kind of what I've learned through all these various experiences, science policy, as I mentioned, kind of impossible to explain, but it's really about working at the science and society interface. On climate policy specifically, we really need both top down, so at the international federal level, and really bottom up approach and policies to really drive climate action. And, I can say this, having worked with farmers and ranchers on the ground, but also working at the international level and national and under two very different administrations. And the current administration's whole of government approach really requires scientists working at all scales and sectors. I like this quote from the latest executive order on tackling the climate crisis, that domestic action must go hand in hand with US international leadership aimed at significantly enhancing global action. So, Secretary Kerry is flying around the world and really trying to get our partners to enhance their global ambitions in terms of mitigating climate. But really, what we say also matters, and how we prove to folks in the international stage that we're going to do what we say is also important. So that's why, domestic goes along with international. And I'd like to thank you all for your attention. I talked a lot, and so I want to allow some time for questions. Thanks.
Great talk. Thank you, Julian. So who wants to lead with the first question? We have Richard with a question.
Sure, very nice, Julian, thank you. If you could speak to either old fart scientists like me or young scientists, up and coming scientists, what do you want from them that would most help the important work that you're doing?
That's a really great question, Richard. That's a really big, I think it's important to be able to use your science in a way that is helpful to society, whatever that looks like to you, whether that is engaging with policymakers, engaging with communities. I think now more than ever, we need the public to understand what scientists do and why science is important. And I think very recently we've seen kind of this attack on science and, why should we be funding things through the National Science Foundation? And so part of a lot of the work that I was trying to do is to show this is what scientists do in the federal agencies. We're trying to help you. And part of that work includes being able to communicate your science in a way folks can understand, the societal relevance, the so what. And I think a lot of scientists still miss that because we're so focused on our bench work or getting papers out. And not to say that's not important, but that we should still remember that we're doing this in the context of worldwide climate change, solving the climate crisis. And I just think that we need to continue having the confidence of society in terms of funding research. I think that's kind of the bottom line. And finally, that scientists should not be afraid of engaging, whether that's in the policy sphere or with communities. I think that's also important and ties into kind of building the society, the science society relationship. I hope that answers your question. I have a lot to answer about that, but yeah. I
am sure you do. Just to echo what you said, and this, of course, one recent survey said that almost 90% of Americans cannot name a living scientist. Not even do they not know one, they can't name one.
Wow, that's fascinating. Yeah, and just a quick personal story. My mom, as I mentioned, she didn't even know what a PhD was. I showed her my dissertation. It was a book. She understood it was a book with chapters. And to this day, it still takes me time to explain what I actually did during my PhD. So that's like a work in progress. But that type of building that capacity for scientists to explain to your mom what you're doing, and it's hard. A lot of our work is very technical, and the work I do now is very high level, and I can barely engage with scientific articles, but I think there's a role for everyone to play. I think scientists can be at the bench, and that's great. If you don't want to talk in front of crowds, I still get really nervous, but if you can just at least be able to share your articles with, let's say, someone in the federal government who does that translation work, go ahead and send that. At least you're doing your part in kind of that spectrum of engagement, whether that's with policymakers or communities. And so, yeah, just recognizing that we operate in a society. So.
Hey, Julian, this is Karthik. Really great talk. Thanks so much. Would love to get a copy of your slides because it was so comprehensive.
It took me a while to put together. So many things I wanted to talk about. So that's great.
Yeah. Yeah, no, it's good, but it's, I'm like recovering from the second shot of Pfizer, so not all there today.
That's okay. That's good.
I have so obviously we have AAAS fellows at NASA headquarters as well. So I just wanted to put in a plug for that. I was offered a AAAS fellowship in 2009 and always kind of regret not taking it. I just started a new position at NRAO and had a faculty position in Cape Town at the same time. So I had to make a really tough decision. And it's amazing to me to see how much the program has grown, because at that point, it was 30, 40 people. I mean, it was very small. And so the number of fellows now is just astounding. Yeah, but I just wanted to echo, it's a fantastic program. So I had to encourage everybody to really take advantage of that. Yeah, there you go. So interesting.
Yeah, not to put a spin. Yeah, not to put a spin on why it increased around 2008, but you could make some interpretations.
Yeah, no, that's great. That's really good.
But no, it's actually a very great time to be a scientist, I think, in the federal government. And, you can see this kind of consistent number of fellows. And then actually in my year in 2019, there's actually more positions than fellows. And so a lot of offices are really looking for that expertise and that communication translation role. And not to say that you won't be using your scientific expertise, but perhaps, you can pivot away from what you did your PhD in, but maybe that's okay because you play a different role in that science society interface. And I think it's all about, just finding where you want to be, in the federal government. So it doesn't mean you're tied to what you did in your PhD, because I don't know, I don't do what I studied or researched, and I enjoy what I do now, so.
So I have a quick question for you about USGCRP. The criticism I always hear of USGCRP is that because it is, this partnership of 13 agencies, it really has difficulty actually executing on much. And I'm just wondering kind of what your lived experience was in terms of whether it's an effective organization.
That's a really great question. And actually, a part of my role at the State Department is actually also being the point of contact for a variety of interagency working groups, as you know, which there are many. I do think they definitely serve their role per the mandate of the Global Change Research Act for at least the National Climate Assessment, right? That's produced no less than every 4 years. So they do do that mandate. I do agree with you on that. It is difficult to measure, I guess, their effectiveness in really a lot of the interagency working groups. I do think there's a value for their convening role. And I will say that the hubs, are also a convening partner among USDA and other partners. And I think with USGCRP, it is probably a bit more difficult because it is 13 federal agencies. So there's a hierarchy of how decisions should be approved. And I think it is difficult to kind of parse out maybe the value added of USGCRP, since it is all these various organizations contributing. And then is it USGCRP just putting its stamp on something that's existed? And of course, a lot of these conversations are happening, but it does take time to produce an output. And all these folks are attending these interagency working groups as kind of just on the side. It's not necessarily part of their job, right? It's only because they think they can contribute something of value to a discussion, but in terms of who actually does what they say they want to do, that they only have they have a staff, but I mean, they can only execute so much.
Yeah. Yeah, thanks so much. If you stick around for my talk, I'll talk a little bit and re-amplify your message, your message of, that scientists should shut up and listen. I also was wondering if there are no other questions, if you could just tell people a little bit about Thriving Earth Exchange, because scientists can plug into that at AGU.
That's right. Yeah, actually, I think the program I attended at AGU was the Thriving Earth Exchange, right? And that's a great way to get involved with communities, right? Linking scientists with communities. That's right. Thriving Techs is a great program through AGU. I don't want to take up the next person's time.
Yeah, so don't
Richard?
I did have one. If
okay.
Richard, do you mind if I ask one more question?
Of course not. Go right ahead, please.
So my question was, so I think the unfortunate reality of climate change is that there are some people who do not want to listen to the science. So how do we work with or around that issue?
That's a great question. And obviously I'm not the foremost expert in this, but from my experience working with farmers and ranchers, obviously you lead with what you know. I'm not going to lead with the IPCC's findings. I'm going to lead with what really matters to them, that we're talking about drought, I'm going to lead with having enough water for growing forage for your animals. I'm going to lead with ensuring they have the right resources to, engage with USDA programs. And the problem with that is that it takes time to build trust with these communities, and especially rural communities. And over time, then you can start talking about climate science, climate change. But a lot of these engagements, or how we go about doing this, really isn't made for that long-term engagement. So I was in a fellowship with the USDA Climate Hubs program, but I ended it in 3.5 years. That's not enough time to create those long-term relationships to build trust and begin talking about climate. And obviously extension is really kind of the US's best kept secret. These extension agents really do have the long-term relationship with our ranchers and farmers. And we definitely value and use them as a way to get the climate resources, climate talk, through them, to the farmers and ranchers. And so I think it's definitely still a work in progress, but we, especially during the last 4 years, the climate hubs among all the various climate organizations learned very well how to talk about climate without leading with climate. If you looked at the recent news, you can also see that it's changed from climate change to climate crisis. And that kind of adds a sense of urgency in terms of how we need to get things done. And so I think that's actually a good thing, and that people are paying attention. But of course, that renaming won't probably affect what a farmer or rancher is doing down in southern New Mexico. They're still working the land, making sure they can still feed their family. And so I think we just have to make sure that even if there is this great domestic action happening, a lot of new international goals, there's still the folks on the ground who we still need to have conversations with, and they may not begin with climate, and that's okay. It just takes time. And related to what Richard, when we were talking about, folks don't even know a scientist. So it's about having that first conversation. And, while I do miss flying, okay, flying is bad for the climate. It was a great opportunity to talk to your neighbor. You don't even know what political affiliation, what do they think about climate, but you're just talking. And, talking barely happens now. I mean, we do it, virtually, but it's not the same as in person. And so, like I said, I think it's just important we have conversations, whether it's climate or not, just really build trust.
All right, thank you, Julian. So I hope everyone gives a good virtual round of applause for Julian, and we will get on to our next talk by Dr. Richard Alley of Penn State University. And I believe Beth Ann is still here, and I will let her do the introductions.
All right, well, thank you. So this is Dr. Richard Alley, who I had in undergrad, who was absolutely famous within the realm of geoclimate. He's talked to the Senate and the Congress, I believe, on multiple occasions. He even had his own TV show going for a while just to tell everyone about climate change and his research. But I'll let him talk more about what he actually does.
Well, thank you, Beth. And it is an honor and a privilege to join you. And Henry, your question to Julian there, maybe we should come back to that one after I get done yakking here a little bit, because how we do this is really important. And Julian had some fantastic ideas in there. And so, yes. And if you missed Stipo's first talk this morning, the hard science was really nice. And thank you there. So I'm going to back up to 50,000 feet and take the really broad view. You've been hearing important science. You've been hearing how to use that science. I'm going to try to give you a big overview. You will see my contributions sort of kind of show up in about 2 slides in here and none of the rest. So this is mostly me telling you the story of what other people have done. And I hope that we leave enough time here to have a little discussion. So thanks to Beth, and great to see you there, and thanks to Henry, the New Mexico Graduate Student Association, for putting this together, and thanks to you for who have tuned in and your interest here. Okay, so and the penguin pictures aren't actually relevant; they're just fun. So I used to spend a lot of time on ice sheets at one pole or the other, and so I could. Someday I'll switch and use musk oxen, but for now we use penguins. So there you go. So for what it's worth, I'm old. Right? I started working on ice when I was a rising sophomore at Ohio State in 1977. So I have been at this for a while. Julian mentioned the Intergovernmental Panel on Climate Change. I helped a little bit on the second assessment in 1995 and on the third assessment in 2001 and a lot on the fourth assessment in 2000. So I've been at it. And I got into this as a geologist, a real field geologist, and then I studied metallurgical engineering and material science, and then I went to see how snow turns to ice on ice sheets, and then I could identify annual layers in an ice core, and then I could see how much it snowed per year, and then I was a climate scientist, and I did not intend to do this, but these things happen. And so now we mostly work on ice sheet collapse and sea level rise, but we still do some history. And don't tell anyone, we also do how ice sheets make landscapes, because that's really fun. So at any rate, so what I'm going to do is this big view from way up high. And I'm going to talk a little bit about why our energy use is so important to us, why we love fossil fuels so much, and then why we have to get off of them and what we can do instead. But it's this, how much good we get from them is why this is such a hard problem. And so we're going to walk through this whole story, and we're going to do it as a story, a little bit of narrative. But I'm going to start here, because this is really the important thing. And you already got this from Julian, but let me do it from a different direction. We can still solve problems. There is this tendency to say we can't get together and solve anything. We just have to hate each other. That is stupid. Okay, just blithering idiocy, stupid. And if you want to sort of see it, I have a picture over here on the left of a do-it-yourself cell phone kit. All right, what's a cell phone? It's a little bit of quartz crystals or quartz sand that you get the silicon for the chip and you get the glass. It is a little bit of organic material of some sort, such as oil, that is used for the plastic. And it's not actually these rocks, it's the ones with the palladium and the rare earth elements and what have you. But all it is sand and oil and rocks and science and engineering and design and marketing. And, you know, it's... There's a nice lady in my phone that tells me where to go. My wife uses an Australian guy. He says, "Turn right here, mate." But at any rate, the nice person in the phone that tells us where to go is using GPS, which was a military program. And the GPS is using relativity, because the satellite is higher in Earth's gravity well, moving faster than us. So it's using special and general relativity. And if we didn't understand relativity, the GPS would get lost beginning in about 2 minutes, right? We can solve problems. Science works, engineering works. We can do these things. We can solve energy too, okay? In a lot of ways, it's sort of easy compared to relativity and quantum mechanics and cell phones. So let me do energy. Right, so a human diet, if you just took physics, it's 8,400 kilojoules per day. If you didn't just take physics, it's 2,000 calories with a capital C per day. If you put your 2,000 calories on a table and you burned them over 24 hours, the energy that comes off is 100 watts. All the brilliance that you do in your life is powered by the same energy as one old light bulb. Right? You are way more efficient than an old light bulb, and that's a good thing. Okay. Averaged around the world, though, we get a lot done for us. I do not have to ride a bicycle to make the electricity that allows me to talk to you over this. It's being generated in some other way. And around the world, the average use of energy outside of us is 25 times what we can do for ourselves. In the US, it's 100 times. So whatever I can do, 100 times that much is done for me. And it's plowing and cooking and heating and cooling. And, you know, if I keeled over here, one of you had called 911, there'd be an ambulance would pick me up. They'd take me over to the hospital. They'd probably save my life. And it would all be done with oil and coal and gas. And right now, about 83% of that energy that underlies my well-being and your well-being is from fossil fuels. We love this. Our well-being depends on this use of external energy. Okay. You could tell humans' history from so many different ways, but one way you could tell it is our hunter-gathering of energy. And we have a history, since we discovered how to control fire, of burning an energy source to cook, to heat, to drive off wild animals, to whatever. We burn some energy source. We burn it faster than nature makes more. We breathe what's coming off the fire and we get sick from that. We suffer pollution and other problems. Then we get scarcity. We don't know what to do. We often fight each other. We have other problems, and then we find something else to burn, and then we repeat. And this is one way you really could do our history, is burn, suffer, run out, panic, burn, suffer, run out, panic. And I'm going to show you a little of this for part of the US. So I'm at Penn State. I am just down the road from here. So this is the main road into our town. Our town is called State College. State College is a suburb of Penn State. If you look at their founding dates, Penn State is older than State College. State College grew up as the bedroom for Penn State. What is Penn State doing here? It was founded by the iron masters. So the people that ran this iron furnace were wealthy, and they put a university up the hill just before the iron ran out. And so when you drive into Penn State, you are coming because this is here. And when this was running, it looked more like this thing down here. This one is from Hopewell Furnace. And they were turning red dirt and limestone flux into the iron that built the eastern US. And they were powering it. You'll notice that it's hot down here. They were powering it with charcoal. And this is a picture from the colliers. I sometimes jog around Collier Lake up here. The colliers or colliers were the people whose job it was to make the charcoal. And these old codgers were demonstrating in their old age how they had done it in their youth. Right, so this is a recreation for the photographers, but nonetheless, you get a whole bunch of trees, you split them, you make a big pile of them, you bury it in dirt, you then burn it with restricted oxygen to drive off the water and some of the volatiles. If the dirt happened to break, some poor schmo had to climb up there and fix it and not fall in and die. It's not a great job. And you know what you're breathing is not something that's wonderful for you, but it's ultimately trees. And this is what it did. A furnace, when it was in blast, and the people who took care of the furnace took about a square mile of mature forest per year. So if you can think of going to a mature forest, eastern sort, not something sparse, not an open ponderosa woodland, but an eastern full forest. Walk for 20 minutes, turn 20 minutes and come back. That's enough trees to run the furnace and the people for a year. And then you got 50 years until it grows back and you can do it over again. And you need another square mile, and then another square mile, and another square mile. Okay. If you go to a map of Pennsylvania today and you say, where do we remember the name furnace? Where are furnaces still on the map? Every line over here on the left is a furnace. And the one I showed you is on this list. There's a whole bunch more furnaces back in the woods that we've forgotten about. They're not on the map anymore. They've been abandoned too long. But every line on here, when it's running, is a square mile of trees per year. Now you take, these made what they call pig iron, just blocks of iron. You take that and you'd ship it to a forge like Valley Forge. So everything over here is where we still remember a forge. And the forge makes it into useful things. So every line on here, plus a bunch more lines you don't see, is a square mile of trees per year. And this is just for iron, right? We're using trees for a lot of other things. We're from Pennsylvania. This is Sylvan is woods. This is Penn's woods. They said that when the first European settlers came to the coast of what is now the USA, that a squirrel could have gone up a tree on the Atlantic coast and stayed in trees to the Mississippi. And the squirrel can't jump the river, but you could get all the way across in trees. The first forester of the Commonwealth of Pennsylvania was someone called Rothrock, and he wrote about the Pennsylvania desert. Now, it wasn't a desert, it still rained here, but essentially the entire Commonwealth of Pennsylvania was treeless. We cut them all. There's little tiny pockets that got away because we had really crappy surveying and we had really strong laws against stealing your neighbor's tree, which is the kind of thing that happens when scarcity arrives. You're not allowed to, governments become interventionist when it's scarce. But we just cut them all. There are now 1 million deer in Pennsylvania. There might have been a few left, but they were basically none. We have elk because we re-imported them from the Rocky Mountains. We got rid of our elk. We got rid of our bison. We got our schools and Nittany lions. There are no Nittany lions. For a while, there were no deer to eat. There wasn't a tree to do it behind. Pretty much, if there was something bigger than a rabbit or a squirrel, we got rid of it. And it wasn't just us. It's lots of China, it's lots of Europe, it's a whole bunch of other places that we burned through the trees at a fantastic rate. And then we hit all kinds of other problems and government interventions and all sorts of things. This is, if you think of my arm as Cape Cod, first encounter between pilgrims and native persons was at Eastham, which is right there. In the 1600s, not even up to 1700s, the town of Eastham outlawed your own ability to cut your own tree on your own property because deforestation was so extreme, they didn't know what to do. Okay. Now, if you've ever tried to read by firelight or a candle of a dark winter in a Pennsylvania, far north, it's pretty hard. Poor people used to use a biofuel, a lamp fuel called camphene. It was alcohol and turpentine. It was pretty cheap. It burned cleanly. It gave a bright light, but it was sort of like white gas. It tended to blow up. And there's horrible stories of the Methodist minister and his wife go out to visit the parishioners, and the daughters try to refill the lamp, and it blows up and burns down the house and kills them all. Rich people used to burn whales. So you take large quantities of money, you ship it to New England. New England uses it to put people on sailing boats. They go out and they kill whales and they cook them and they get whale oil, and it burned clean and it didn't blow up. So it was a safer thing. So there's all of this, let's go kill all the whales we can kill. This is the history of whale oil production in the Yankee fleet from 1800 to 1880. This is a complicated history, right? There were some whales that the sailing boats couldn't get to, and those were killed by Norwegians and Russians and Japanese over here with diesel and harpoon cannons. But basically, this is a story of killing all of the economically useful whales in the world ocean. We basically, if you could find enough of them to make it worth sending out a ship, we pretty well killed them. At the peak, so as they got better at killing whales, the price went down. they're learning. This is about $7 a gallon in modern money. The price started drifting up as the whales get scarcer. The fleet gets crushed in the sea ice off of Alaska and the insurance goes through the roof. But what was the fleet doing in the sea ice off of Alaska? They couldn't find whales they could kill closer to home. And so they hit peak whale oil here. And what happened then is, as it gets really hard to get more whales, the price goes way up through the roof. So $25 a gallon in modern money. And so there's your history. At peak, there are 10,000 sailors on whaleboats. 10,000. Now, if you take all of that, 10,000 sailors at the peak, 100 years of Yankee whaling, if you could take all the oil from all of that biomass and put it to use today instead of rock petroleum, it would last 11 hours. 100 years of whaling would last us 11 hours. The idea that we go back to biofuels when we start running out of fossil fuels is just complete ludicrous. But this thing, the price goes up through the roof because they're running out of whales. And then somewhat later, not too much, for thousands of years, humans had been using oil that was leaking out of the ground in Pennsylvania. They used it for waterproofing water carriers or waterproofing boats and things like, and in other ways. But oil was leaking out of the ground. And so Colonel Drake says, wow, if oil leaks out of the ground, maybe there's oil in the ground. So there's the first modern oil well. And be very clear. We have trees and whales now because we let them grow back, because we switched to burning oil and gas and more coal. And it's that easy. We let grow back what was a completely depleted resource because we switched to burning something else. And we had all kinds of panic and worry before we found this new thing. This is not a new idea. This is an editorial cartoon. It was published by the magazine Vanity Fair in the year 1861. So this is just before the US Civil War. And the title of this is across the top there. It is the grand ball given by the whales in honor of the discovery of the oil wells in Pennsylvania. And you can see sort of oil's well that ends well. We wail no more for our blubber. This is right before the US Civil War. So the oil wells of our native land, may they never secede. We have whales and trees because of oil and gas and coal. And the trees and the whales mostly grew back in 100 years. There were a good many problems until they get back. The fossil fuels will grow back in 100 million years. You meet the person who says we have to choose between a renewable energy system and a fossil fuel system. This is total nonsense. We have two choices. We can burn and then learn, or we can learn while we burn. And there is not another one. But if we burn before we learn, we really do know we'll change the climate. And we know we'll change the climate in ways that we really don't like. So that's what comes next. The idea of global warming from CO2, right? The greenhouse effect is figured out by Fourier, the great French mathematician, behind Fourier filters that make the GPS talk to your phone. Greenhouse effect is figured out in 1821, role of CO2, Tyndall, 1859, warming from fossil fuel CO2, Arrhenius, 1896. The modern quantum mechanical understanding of the physics underlying global warming came from the Air Force after World War II. They were doing things like heat-seeking missiles. Up in there's infrared. And most of the infrared is from the sun heating the earth and then the earth sending it back to space. Occasionally, a little of the infrared is from the hot exhaust of an enemy bomber. And the Air Force said, you know, infrared gets absorbed by CO2. If we put the wrong sensor on our heat-seeking missile, we can't see the target. And so they figured out the physics of how a molecule of CO2 absorbs an infrared photon, and then it wiggles or it wobbles back and forth, and then it collides with an oxygen or a nitrogen and transfers that energy to the other one, and then it absorbs more infrared. And they figured out all this physics. And because there's so much more infrared from the sun-warmed Earth than there is from enemy bombers, this makes global warming from more CO2 completely unavoidable physical fact. Before they ever launched satellites, they predicted what the satellites would see when they looked down. They were right. This is a spectrum. This is the energy going up to the satellites from the sun-warmed Earth in the infrared. And this is what's not getting out because CO2 is up there making a greenhouse effect. And if there's more CO2, it can absorb more. We're seeing the changes in the radiation arriving from our change in the atmosphere from burning fossil fuels. This is just observed fact. This one's interesting. So 1980 is on your left, 2020 is over on your right. This is related to the IPCC process, which brought a whole lot of this into being. And so you have CMIP ensembles from the SRADs. This is all IPCC speak. Various groups with different funding sources, including private funding, on different continents have estimated the history of Earth's surface temperature. The different colored lines on here are those different estimates, and you'll see that they agree. And what you see is basically an up and down from El Niños and La Niñas and changing sun and volcanoes blocking the sun, and an up and up from CO2 primarily. And what's in here, the black line is an average from a whole bunch of models. And starting here, it's a prediction that was made, not an explanation. So back here, it's an explanation. Up here, it's a prediction. So the models predicted the black line. What then happened are the colors lines. This works. It is predictive as well as explanatory. It is physically unavoidable. This is all real. So like I said, and it's not surprising, Arrhenius more or less had the physics right in 1896, not quite, but pretty close. Arrhenius completely screwed up on the economics. He didn't think we'd ever burn that much fossil fuel. He didn't think fossil fuel companies would be as good as they've been at getting us what we ask for. Here's a scaling, just you know, a coal tanker, a coal train is full of stuff. You burn it, it's still stuff. An oil pipeline is full of stuff. You burn it, it's still stuff. We all sort of know what stuff looks like. We throw it away for the trash collector. In the US, per person per year, we throw away for the trash collector a half a ton of trash. Our share of the CO2 from the energy system is more than 16 tons. So if you can imagine, you've seen trash, you've been behind a trash truck, you've taken trash out to the curb for the trash collector, you've thrown trash away in the room. Trash, a half a ton, CO2 more than 16 tons for a year. And it is changing the climate. This is real. Okay. So let me now do a little bit of good news after I do some more bad news. Okay. So if we don't use this knowledge wisely, if we continue to burn more than is good for us, where are we going? A little bit of change was not terribly bad, to be honest. So the coming changes will be bigger than what we've done so far. The past changes really have had winners and losers. A little change wasn't too expensive. The coming changes will be mostly losers. The costs go up faster than the temperature. First one was almost free. We did it. Second one will cost more. We're committed to it. Third one, mostly committed. Maybe we'll stop at 1.5. But at any rate, the third one will be really expensive. Okay. And the uncertainties are heavily on the bad side. If you don't trust me, you should be more worried about this. It could be a little better. It could be a little worse. It could be a lot worse. So let me show you a few of these. Right. This one may be as big as anything, the heat stress on people and crops. You would never, ever, ever lock your little dog in a hot car in the sun in New Mexico on a summer day without an air conditioner because it's fatal. You don't do that. There's no place on the earth today that is hot enough outside to be necessarily fatal to people. You students could live to see the day that that happens, that you're outside naked in the shade, in the wind, drinking water, and you're going to die of heat stress. That's possible in your lifetimes. Way before that, it's really hard to live in a lot of those places unless you have air conditioners. And if right now there's a lot of people in those places that don't have air conditioners. So you get heat stress on people, you get heat stress on crops. I'll show a little of that. Sea level rise, virtually guaranteed. When it's ready to rain, warmer air has more moisture, it rains faster, you can get more flood. Every clothes dryer, every hair dryer has a heating element because it dries faster. You can dry out faster. There's more evaporative demand. You can get more droughts. The more energy to power the strongest storms. You lose one line of defense against some diseases. You're trying desperately to keep your rare and endangered species alive, and they have to migrate either up the mountain and off the top or north across places that we humans have taken over. So there's a huge danger of extinction, ecological stress, and it especially hurts poor people in hot places who are not causing it. So these are just data. They're just correlations, but they are correlations for which we have pretty clear idea that it is caused. So you go to a poor place that doesn't have a lot of air conditioning. You look at what happens as it gets warmer. How fast do people die? And more people die when it's warmer. You go to the tropics and ask what happens when it gets hotter, and people fight each other more. You ask what happens to crop yields. We tend to grow our crops fairly close to the optimum temperature for them. If you make it colder, that's not great, but it's not a big drop off as long as you don't freeze them. If you make it warmer, it's pretty bad. We're going to make it warmer. This is Syria, civil war, 500,000 people dead. Do not for a minute think that climate change caused the civil war in Syria, but drought was a contributor. A drought hit the Mideast. Most countries handled it. The least happy country did not. They started shooting instead. And we humans have already loaded the dice to come up drought. We made the drought 2 or 3 times more likely. The drought happened. It contributed a stressor, which with a lot of other stressors led to a very, very bad outcome. Now, this is, by the time you students are old, what happens to drought if we don't change our energy system. Green is less drought. Now, I want you to note that you're still not farming in the Sahara. No, that's still not there. But what you'll notice, whether you out here or us up here, virtually all the people in the world live in a place that you expect more drought with warming. And where drought is already implicated in bad outcomes, lots more drought. Okay, that doesn't make people happy. This is Fort Lauderdale. I swiped this picture from down here under fair use. I didn't take it. This is not a canal, it's a street, right? You can see the driveway here. This is not a storm, it's a high tide. This is what they call adaptation. You have a street that you shouldn't be driving on because you'll splash water on the trees and kill them because they don't like salt because it's salt water. So for a while you don't drive here and you put up a no wake zone sign. This is a parking garage in Miami, same story. This is not thrown in here by hockey fans. It swam in. It is not a storm, it's a high tide. This is what they call nuisance flooding. The flooding is a nuisance. And then at some point, it will not be a nuisance. It'll get really expensive. And as I said, the price goes up faster than the temperature, beyond some threshold, now you have to keep the salt water out of your drinking water, or you have a real problem. And now you start thinking in billions and tens of billions for one city. And there's a lot of cities. And then this is the uncertainty thing. We work on this all the time. So this is Hurricane Gustav that did not get in New Orleans. I would not have wanted to be this peace officer, but this is one that stayed behind the wall. Sea level rise that will require raising the wall is pretty well baked in already. We're going to have to do some changes. But the uncertainties on that rise, it's sort of 3 feet by the year 2100 under strong warming, and it could be 2, and it could be 4, and West Antarctica could collapse, and it could be 15. Okay, 3, 2, 4, 15. And that's sort of the way the uncertainties go. It could be a little better, it could be a little worse, it could be a lot worse. And we see that in a lot of ways in this story. Okay. So this is us with the UN. We were engaged in this hashing out every semicolon in the summary for policymakers. They locked us in the UNESCO complex in Paris, and we're locked in. Paris is outside the door, right? Around midnight, they brought in these little sandwiches wrapped in plastic, and that is dinner, and Paris is outside the door. But at any rate, you know, so the UN Intergovernmental Panel on Climate Change has been assessing the science, the implications, and the options for a very long time. They have generated, if you printed it out and piled it up, it'd be 15,000 pages or something. It's just the mother of all committees. It's just truly amazing. If you took everything in those documents and you turned it into a tweet or two, it's this. Think of 2 futures, one in which we ignore what we know, one in which we use what we know efficiently. Using what we know efficiently gives us a better economy. It gives us more jobs. It improves our health. It improves our national security. And oh, by the way, the environment is cleaner and it's more ethical. Right now, economy and employment and health and national security are in the same direction as ethics and environment. William Nordhaus, I served on a committee with him, professor at Yale, co-winner of the Nobel Prize in Economics in 2018, for building tools that allow decision-making on how much to consume, how much to invest broadly, how much to target investment. All of the uses of this now are consistent. We are hurting ourselves economically because we're not targeting enough investment at reducing climate change. You'll meet the person who says, yeah, the climate is changing, but we can't afford it. The Nobel Prize in Economics says you can't afford not to deal with it. That sort of economics assumes we don't have civil wars like Syria, and we don't have ice sheet collapse like West Antarctica. You get some of these tree huggers that you might run into, you know. So here's JP Morgan, good tree huggers, right? And they said, you know, we shouldn't just be looking at that central estimate that says we're not investing enough in heading off climate change. You also should look at the possibility of the tail events, the black swans, the tipping points, the ice sheet collapses, and the civil wars, which would mean that we should do more now to slow down climate change. Okay. Jobs, it's harder to get good statistics on jobs. Guarantee fossil fuels make good jobs. A lot of people like them. I worked one summer for an oil company. I still trade Christmas cards with my supervisor there. Our students have gone to work for oil companies. There's good jobs there. But it's fairly clear that anything except fossil fuels tends to generate more jobs. And that's partly because, probably, because more of the price of the fossil fuel goes to the control of the resource, not to making the resource useful. The cheapest fossil fuel producers in the world can put oil on the tanker for $5 a barrel. That $5 pays for jobs for someone. The other 45 is because they control the resource, not because they made the resource useful by hiring workers to do the job. Health, a whole lot of people get sick from breathing bad air. Bad air is caused in large part by burning things. The biggest burning we do is fossil fuels. So you have a whole bunch of medical groups here who said the most important action we can take to protect health is to accelerate the inevitable transition to clean renewable energy. There was one study, and this is maybe on the higher end of the estimates, but one study said 1 in 5 deaths, 20% of the people who die in the world died young because they were breathing bad things coming off of fossil fuel burning. That's one study, but that's worth thinking about. Military leaders, people who have looked at destabilization there, which makes people mad or makes people migrate, that makes people unhappy, and said, look, we have to deal with this. We have to adapt to it, but we also need actionable agreements on ways to stabilize climate change for national security. Extinction, right? This is an old paper. These have been confirmed since. If we don't change our energy system by the time you students are in the middle of your careers, we've put maybe 1/3 of the species on Earth on the route to extinction. Ethics, red in the top is a lot of CO2 per person per year. Red in the bottom is highly vulnerable to the warming. Red at the top is changing climate. Red at the bottom is suffering from the changing climate. Pope Francis doesn't like that. Neither does Jimmy Carter or a whole lot of other people. So wise action, efficient action helps the economy. It helps employment. It helps health. It helps security. It helps the environment. It helps ethics. All right, what can we do? This is a tiny bit of the solution space. I'm not saying these are the answers. I'm showing you what's possible. 2,000 calories per person per day. Where does it come from? Everything in color on here. Top is crop, bottom is grazing. Everything in color on there, we have changed to get 2,000 calories per person per day. Suppose we decide to use existing solar technology, the kind of stuff that's on the roof over my head here, to replace every bit of energy used by every human on Earth, and then to include some extra so we can grow a bit. Existing technology, more energy than is used by all humans on Earth from all sources. Just for reference, I'm going to put it in the Sahara. You know, some of it's going to be on your roof, but that's it. That's more energy than is used by all humans on Earth. Now, don't kid anybody. That's 30 years of building. That's it's really, 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 really big compared to our roof. But is it possible now? Sure. I did these TV shows, wrote a book, and I got to make some TV. We just had an amazing time doing this. It's 10 years ago. It's on PBS, and then it went into various other places, and there's been sort of 40 or 50 million people have seen it, so nobody saw it. But at any rate, in doing it, we went down to Texas and we talked to these ranchers, and the ranchers had put 5% of the land into wind. They kept 95% of the land in land. But the wind pays better than the rest of the ranch. And they saved the town, and they saved the high school, and they saved the ranch. They call it mailbox money. They go out to the mailbox and they get money. If you put a wind farm on the windy parts of the plains and deserts of the world, that's about 5 times more energy than humans use. It's a big wind farm. But is the resource there? Sure. You might have seen this, International Energy Agency 2020. We now have the cheapest electricity in history. Renewables can make electricity cheaper than anything that's ever been done before. I'm really excited by this. I don't know where it will go exactly, but there's this brand new idea, not brand new, but fairly new, agrivoltaics. In some places, some crops, if you put solar over your fields, you get money from the solar and you get more crop. And it's not all crops and it's not everywhere, but some crops like part sun rather than full. If you've got an irrigation canal and you put the solar over the canal, you have less evaporation and the solar is a little cooler and it actually works better. There's people working on things like growing peppers that actually grow better under the solar. If you're water stressed and you reduce evaporation, that can help. And if you're a farmer and you're having troubles affording the farm because you can't raise enough crops, maybe raising sun as well as food will help you. And if you've got wind, you can have wind and sun because you've got transmission lines. This is from the world's largest independent investment bank. These are not tree huggers. This is cost of electricity, assuming that we got rid of all of the subsidies for the renewables. So we have zeroed out renewable subsidies. And I'm just zooming in here. And so cheap is over here on the left, that's free, and this is really expensive on the right. This is the cheapest energy to add to the electric grid in the US, which is gas. And you'll notice that actually, no, it's not the cheapest. The cheapest is wind and sun. The cheapest gas has troubles competing with the cheapest wind and sun. If you were looking at things like new nuclear or new coal, they're not even anywhere close. The truth is just operating existing nuclear and coal is more expensive than building and operating new renewables in many places now. Now, it's not the full system. It's not an integrated thing with 100%, guaranteed. That's 30 years away. But adding a little electricity to the grid now, the cheapest stuff is renewables. And that's zeroing out the subsidies for renewable, but it's not zeroing out the subsidies for fossil fuels. And this is an estimate from the International Monetary Fund that says that people working with the International Monetary Fund says that the full subsidies for the fossil fuels, include allowing them to change the climate and hurt your health, are vastly bigger than the subsidies for the renewables. So don't kid anyone. Doing this is going to be really hard. It's changing an immense amount of stuff, and it's changing something that has been fantastically successful for us. We do not have all the answers, but we're the first generation in all of human history that knows that we can now do this. It's possible, it's doable, it's economically doable. And we know that we can do this in a way that can help the economy, can help employment, can help health, can help security, can help environment, can help ethics. So I'll leave you with a picture I took in Greenland. Can we really have a world with icebergs and rainbows? Sure we can. This is doable. So thank you for inviting me. Thank you for tuning in, and we'll stop and have a little discussion here.
Great, thank you, Dr. Ali. So we, I'm sorry, lost my train of thought. So who would like to ask the first question?
Hi, Dr. Richard. Kartik.
Hey, and thank you for your talk earlier.
Thank you.
Thanks, Stipo.
Thank you. This was really interesting. There's two questions I have, and the first one's for you, but the second one might be shared by Julian and you. The first question is, you haven't, well, I guess one of my hopes is that cold fusion might be one of the energy sources that we develop soon and have really good energy output from that. Have you researched anything about that, if you can tell us? And the second question would be, you had good arguments about CO2 production that we have in our industrial world, and how would the largest producers of CO2 be incentivized to reduce them?
Outstanding, Stipo. So thank you. So fusion, when I was a student, undergrad, when I was in middle school, we were really excited about fusion. It was almost there, right? And then we had cold fusion. Right. So fusion, the joke is that fusion is the energy of the future, and it always will be. If fusion comes through, big smile, use it, we're happy. But we've been almost there for my whole life, and we're not almost there. There's nothing that's ready to turn on. The hot fusion, the people who are working on that say that if they had the money they want and everything worked right, they could have things coming online in 30 years or maybe 20. But that's a long way. And that's if everything goes right. So and the truth is, I showed you the price on nuclear there. Getting nuclear back to competitive is probably not this decade. Even there, it's just not competitive. They can't run the existing plants now in competition. So, I think that we can hope there might be some brilliant breakthrough and everything works. The truth is, the one that I think is most interesting on the horizon that I didn't include is the possibility of hot dry rock. And I still don't know if that's going to pan out. But in principle, you can take fracking technology, you can drill a hole, you can pump water down it, it gets hot, you bring it back up and it does things. And so the one I didn't mention that has the most potential right now might be in that direction, actually. In terms of how to make this happen, and there's Saruj and Kartik there have put questions in as well. I think that the how to make it happen involves, if we could get to better pricing, it would be good. So right pricing would surely be helpful. And so getting rid of some of these subsidies, that's not going to be easy, but getting rid of some of the subsidies for fossil fuels. So I pay for fossil fuels, I get the good from the fossil fuels, and the community gets the bad. And if we made the price of fossil fuel reflect the good and the bad, we wouldn't build a lot more fossil fuels. And how to do that, I showed a picture of Bill Nordhaus. I served on a committee with him. I think if he were on, he would say that it may be easiest through the international trade system. So if a reasonably large part of the world economy decides to right price their fossil fuels, they can then say to the rest of the world economy, you can right price your fossil fuels, you can raise the price, you can keep the money, you can do anything you want with that money. Or we will put a tax on everything you buy or sell between you and us, and we'll keep the money. What would you like? Do you want to put a price on your fossil fuels and the money's yours? Or do you want everything that goes into and out of your country to be taxed and we get the money? And the economists say that'll get you a lot of the distance. After that, I think it really goes into Julian's world. So Julian, you may want to chime in here in a moment, but there is an amazing number of things that we have built that make it easy to have fossil fuels and make it hard to have alternatives. And getting rid of all of those things that are down in the, please don't bore me with this, but it's really fascinating and important, is the kind of thing that needs to be done. There's a million of these, but one, my house was built with a local zoning code, which is framed after a national and international zoning code, which makes sure that the house is safe for a car that has fossil fuels. So the garage has standards for not venting into the house and giving me carbon monoxide. The garage does not have a plug for an electric car. And the zoning code still doesn't say that new houses should have a plug for an electric car. And if it did, right, what would we have? First, it's wired in, it's cheap. I can get the electric car, I can plug it into the batteries on the roof. Now, if we have a power outage, if we have a disaster, I can run things in my house off of the batteries in my car. I can't do that now without a big investment because no one put one of those suckers in my car, in my garage when they built it. And there's lots of these things that make it hard to do a new energy system because they are optimized for an old energy system. So Julian, and I'll try to answer you in a minute, but do you want to chime in first?
Can you hear me? I'm outside.
We can hear you.
Coming through great.
I was just listening a little bit. I think I may have asked the question. I think, just trying to think, in terms of my world, I do think a lot of the things I'm seeing is that it's a whole of government approach, whole of society approach. And in the last administration, there was a lot of talk on kind of a balanced approach at economic, sustainable development and environmental protection. But I think this current administration is really trying to go big. But, you know, as Richard, you were talking about, it is really hard to develop a lot of new things. And as you can see in the current, you know, I'm thinking about how do you pass legislation and kind of get at a lot of these big things. It's really hard, right? If you're looking at this Build Back Better legislation, they're thinking about already doing it through reconciliation, which would require only, you know, 50-50, and then hopefully Kamala will be the time, you know, breaking vote. But that 50-50 legislation, you know, a lot of that will be moderated by the moderate Democrats, of course. And so that's how I'm thinking about this. I don't know if that's getting to your question, but I think that we can get a lot of things done, but I think it'll still be difficult.
Well, I guess, Julian, what I was trying to ask is, the biggest producers of CO2, for example, China, they don't seem to want to at any time soon stop producing CO2. They seem to be ramping up, building more coal electricity producing factories. So how would the US incentivize them to go greener? Or is there something like that they're trying to do with the Paris Accord, which seems to me to be non-committal? They don't have to commit.
Yeah, that's a good question. Yeah, I mean, yeah, the Paris Agreement was initially, I mean, when it was first formulated, it was essentially China and the US, right? Doing a lot of the backdoor dealings. And now it's the US, it'll have to be the US and China really to describe the details and how we achieve a lot of these goals. I think it remains to be seen what that relationship will look like with China going into the future. And, you know, I think, I know Secretary Blinken met with some folks from China, and it was a little frosty. I think it was a few weeks ago in Alaska. But I do think it'll have to be China and the US really hashing out a lot of details as we are the top emitters, right? I think another issue is how developing countries view the US and whether we're actually in a role to finance a lot of the adaptation and mitigation needs, right? And I think in the latest presidential budget, which was released today, I think it said that the US was going to put in at least $1 billion into the Green Climate Fund, I think. And so that's showing that we are ready to play and pay. But I think that will be an issue that China will use against us, is that our past emissions, right, play a huge role in where we are today, even if the US is slowly reducing our emissions. So yeah, I'm not really answering your question, as I can't foresee what that relationship will look like, but definitely China will use its role as a developing country, quote unquote, and especially looking at our past emissions.
Right. So Europe is big. If the US gets on board, China ultimately probably will too. I think there's a lot of feeling they will, and that we can do it with the trade system. So then very briefly, there's a bunch of them over here. Suraj, I think it is there. Right now, with renewables not subsidized, they are starting to compete. If we were really good at getting rid of the hidden barriers, and so it could be done through Julian's side of the world, it can be done through an economic and tax side of the world. So I think it'd be easier if we right price it, but it may not be necessary anymore. Julian had asked about carbon capture and sequestration and storage, geoengineering, huge areas that we don't have time to get into. But basically, carbon capture and storage is going to look really expensive for a long time, I think. Given how cheap it is to generate renewable energy now, the only way you can think of carbon capture and sequestration working is to build lots of renewables to give the energy to do the job, I think, because otherwise it just gets really expensive. Geoengineering, this is, you know, so we could fly 747s around in the stratosphere and block the sun by spewing out particles, the way volcanic-like particles in the stratosphere. And we could sort of kind of offset the global warming. It's not CO2 negative. It's more complicated. It does nothing for ocean acidification. you're looking at, if you put the stuff up, make it really hot and then cool it down, well, you have to do this for 10,000 years and beyond. And if it breaks, you get all of that warming in a big hurry. So you're committing to 10,000 years of doing this, and you're committing to everyone agreeing in the world, at least everyone who could shoot down a plane, to where you're setting the thermostat and to keeping it there. And you're committing to, we're confident that 1,000 years from now, Russia won't decide to shoot down the planes. And if they do, then there's the biggest abrupt climate change in history that's a total disaster. And so I personally am not a huge fan of this. I think we need the research at least to show what would be involved if that happened. Kip had asked about
Can I interrupt for a second?
Yes.
Kartik has had his hand up for about 5 minutes. So
I'm sorry,
let's
go,
get to him
please.
first.
Yeah, thank you. I was afraid to interrupt there, but Richard, I really enjoyed your talk the first time at the AGU and enjoyed the repeat of today. So I hope I keep hearing this talk because it's so good. It's so comprehensive. And I always use your examples of what the East Coast would have looked like, and I think people are always shocked to hear what the East Coast really should look like compared to what it is right now. I have a subtle question for you. I think you painted a picture that I think is very optimistic. And I'm just to be devil's advocate and be a little bit more cynical here. When you say that 1 out of 5 deaths will be from air pollution, remember that that's not going to be equitably distributed. It's mostly going to be Black and brown communities that suffer the most. Similarly, you went through the chart very quickly. Africa, all of Africa uses 1 to 2, 3% maybe it produces the greenhouse emissions. And then to say, well, let's make an international policy and everybody must, adopt the same solution. That's where I think we get into the reality of how this can actually work. So mathematically, as a scientist, I agree with you. Yes, we can solve this problem. I think when we start involving the human aspects of it, I think it's going to be much more tricky. And so I was just wondering if you've started to think about bringing that aspect of why this is important in terms of environmental justice, racial justice, affecting those who are most affected, and using and motivating that argument. Have you thought about that? Have you done that?
Yeah, I think you're completely right. I suspect that the ethical, the racial justice, the ethical justice arguments are actually the strongest ones. But they're ones that we've had a remarkable amount of difficulty getting traction with, because the people who get them are already on board and working hard to solve the problems. And you know this, and if we can find a better way to do this. In the US, my suspicion is getting to the, so you probably know Catherine Hayhoe. She's a climate communicator, she's a climate scientist, and she's married to an evangelical preacher, okay? And this gives her a voice that many people don't have. A lot of the objection to doing something about climate change comes from people who actually are ethically very grounded, but they have rejected our science for reasons that we can't fully suss out. And so I think that we need to revisit this, because I do think that, I mean, you know the story as well as anyone does, but the economics says we're going to change the climate for 10,000 years. And we're worried about the damages for the next 30. And then we don't care much, either because the economy will be so huge that our rich grandchildren will solve all the problems, or because we just don't care. Right? And we're hurting poor people in hot places, but they're economically not very important. So what's the big deal? Right? I mean, this is in there. And when you say it fairly bluntly, it just sounds like, how can you sit there and say that with a straight face? It's just, yes, I was on a panel once with a person from a small country, a poor country in a hot place, and we had the economics discussion and we had the efficiency discussion, and she said, but you're killing our people.
Yeah.
And we are.
Yeah, I think that people like you and you know the rest of you who work in this area, I think you have such a good stage. It'd be really great to start integrating these arguments, the ethical arguments and the disparate outcomes argument, to appeal to people who may not have bought into it. So I
Yeah.
think us as scientists, like trying, well, as Julian said, you know, us trying to just pour knowledge down the brain and trying to say, oh, here's more information you should change. It's just it's not the right way to go. We got to figure out a way to appeal to the emotion.
Yeah.
I think that was
Henry,
Yeah,
right,
now
Henry,
let's
we're-
jump back to Kip's question, I guess.
okay, yeah. So and we'll get through here quick and get off. So I sort of kind of suspect that with the system equilibrium times of the economy as well as the environment that we probably are past 1.5 already, but I still keep hoping. Okay. So we'll hope. Okay. So I don't know, Henry, we've run over here a little bit.
Yes, we have. I mean, if people want to stay on and keep asking questions, that's okay with me. But I know people also want to get lunch. So,
Okay.
or
And
at least out
we
here
are
in
having
Mexico, it's lunchtime.
we are having a discussion at the end, aren't we?
Yes, so we can
Okay.
continue there as well. And I'm sure some questions will come up again. I've seen new people come in throughout the day. So,
Great. Okay. Well, I will drop off then because I'm going to go hear a grad student who's giving a talk in our graduate student seminar. So thank you. We'll see you in a little bit.
thank you, everyone. And we'll reconvene at 1 Mountain Time. Right. Thanks.
Hey Henry,
Oh, yes.
I have a class that I need to go at 3, so I will be off for 3 to 4, but I'll join you right at 4 my time, so 2 o'clock.
Oh, that sounds good.
And then if the audience remains this small, if we can go to the breakout rooms, I would appreciate that. Just
Yeah,
because I have time to break.
yeah, I was thinking of
Yeah.
changing the format probably between the downtime. That'd probably be a good time to do it. It doesn't look like we've had any issues so far with people jumping in, but doesn't hurt to be cautious.
Yes, we had I run I oversee a bunch of economists at a think tank called Resources for Future, and our very first virtual community of practice meeting, we got Zoom bombed. So I'm really bad.
It's like, I haven't seen it in person, but I also don't want to see it in person. I'll just do my best to work around it.
Yeah, makes sense. All right, see you later.
Yeah, see ya. And see everyone else at 1 o'clock.